record on this. And got it. And got it. Okay, well. So it's 8 o'clock and got my big thing of coffee. And close this down. So the first thing I'm going to ask is, does anyone have any questions from yesterday? Yesterday was a lot of material. Yesterday was, to be honest, yesterday was the heavy day. Today is a little bit lighter.
Sometimes a little slow on the uptake. I still have, I mean, I've done decibels with using the computer and 10 log, but your method there is pretty close. I was just wondering if you could go by that one more time, because I
which part of it? The whole, just the calculation method?
yeah, just to, like the 10 dB and the 3 dB, and then you add them together. I lost around the axle or something.
Yeah. Okay. So, all right. So 10 log base 10 of P2 over P1. So that, man, that is some terrible handwriting this morning. Let's start that again. My apologies, everybody. It's early. 10 log base 10 of P2 over P1. So that is the definition of decibels. And it's decibels, deci, because of the factor of 10 thrown in. So what this ends up doing is, whatever this ratio is, you end up getting a number for. So what we're going to do is, like you were saying, we're going to break this up. Okay, so we're going to say that we're going to use P3 and P2 and P1. So P1 is our starting point. We're going to say that it's 1 watt. P2 is 10 watts. P3 is 100 watts. All right. So what is the jump in times P2 compared to P1? That would be 10x. And from P2 to P3 is another 10 times, right? Okay.
Yeah, got that.
Okay. So if we were to figure out the decibel gain from, it's 10 log 10 from overall P3 compared to the starting point is 10 log base 10 of 100 divided by 1. Right? Well, 100 divided by 1 is 100, and the log of 100 is 2, and that would be 20. So I could also write this as, okay, I'm going from P1 to P2 and then from P2 to P3.
So the calculation that the way I looked at it is always just count the number of zeros.
Yep.
Multiply it by 10.
Yep. Exactly right. And every time you do that, that's a 10 decibel gain in power. So, but I could also write this as, so the total decibel gain is 10 log base 10 of P3 divided by P2 plus 10 log base 10 of P2 over P1, because it really just involves starting and ending points, right? Well, this is 10 and this is 10 because you did it twice. You went up by a factor of 10 and then another factor of 10. And this is 10 plus 10 is 20. So you get the same answer, whether you make multiple steps or just one big step, which is why I can at the same time say, okay, well, 13 decibels is 10 decibels plus 3 decibels. This is a 10x gain. And this is 3 decibels is how many times? 2 times. And 10 times 2. So 10 times 2 is then 20. And that's how you get a 13 decibel gain is 20 times. Does that make sense?
Yeah.
Okay. Any other questions from yesterday?
Hey, Scott.
Yeah.
You mentioned an antenna design book early on in the training yesterday. Do you recall the reference on that?
There's a couple, actually. There's the ARRL handbook, which is kind of like the Bible of, which is sort of like the Bible of practical RF design. So that would be the handbook, which eventually will open, hopefully. Here we go, the ARRL handbook. And but there's also the ARRL antenna book. Then they also have antenna compendium and things like that. Antenna book for radio communications. So there's just antenna physics. This is actually antenna physics book is actually halfway between practical use and a college level antennas class. Was written by a guy who actually lives here or lived here in Eugene. He's since moved to Spokane. But basically, they're not college textbooks. They are practical applications, practical application books for figuring out how to build an antenna, how to build something that works using a lot of experience. So here, antenna theory, design, and practical treatments. So there's also another really good book that's written by Ward Silver of the ARRL, which again, I recommend joining just because it's a good organization. ARRL Grounding and Bonding. And notice it's only $22. And this is it's a fairly easy read. It's only what, 100 something pages? Oh, something like that. It's not like, a book that's 3 inches thick, and it's actually a really good book. And grounding and bonding is one of those areas that, okay, so here, let's think of this. We know for a fact that grounding is important, right? Why do we think of grounding as being important? What is ground?
A direct
Ground is a
path.
return path.
Ground is a return path to Earth, but it's not always the desired path, but it is a return path to Earth, which is 0 volts. So the interesting thing about ground is that there are actually 2 kinds of ground. There is this ground, which is Earth, which we think of as a safety ground. And that means basically you've got a piece of equipment and there's a fault when, one of your hot leads in your equipment shorts to ground and either blows a fuse or something, or your ground fault breaker comes into play. Or there's another kind of ground, which is basically here's your equipment and here is your ground. And this would be your RF ground. Now, why are these different? Let me ask everybody a question. So let us say that this ground line, this wire is, let's say, 100 feet long. Okay. What is the frequency of our wall voltage? If you stick if you stick a meter into the wall and you measure your power coming into the house, what is the frequency of that wall voltage? 60 hertz. Okay. Well, we are smarter now than we used to be, right? What is the wavelength of 60 hertz? 300 million divided by 60 is 5 million meters long. Okay, and what would a quarter wave on that be? 1,250,000 meters, which is 1,250 kilometers, which is approximately the distance from, let's say, Oregon to Salt Lake City. So in order for that wire to function as any kind of antenna, to the point where your ground was somehow at a different potential because you have a wave on it, and be unsafe, it would be about, let's say half of that. So let's say it's 400 miles long. You'd have to have a 400-mile long wire for that to not be ground anymore. So not a problem, right? Okay, so now let me ask this question. That is our safety ground. That's for power. Here's the other question. Let's say that we're operating on the 10-meter band. What is the wavelength of 10 meters? Not a trick question. Just the wavelength of the 10-meter band. I just gave you the answer.
10 meters.
10 meters. Okay. So let's say that if we were to draw our waves, this would be 10 meters long, which is about 33 feet. Okay. So if we were to draw waves on this piece of wire, remembering that every wire can function as what?
Antenna.
An antenna. Yeah. Okay. We separate it into 33-foot sections, and here's our wave. Here's our wave, and here's our wave. Well, we might get lucky and find that we are at 0 volts here and at 0 volts on the other end. We might also, at a slightly different frequency, not be so lucky and find that our wave actually looks like this, starting at 0, because we're at ground, and find that compared to 0, we're not at 0. Well, okay, if we're not at 0, how good of a ground does it work as? Is it at 0 volts? Because remembering that the definition of ground is 0 volts. So is our case of our radio at 0 volts anymore?
Yeah.
It is not, because by definition, this wire is now long enough to function as an antenna, and it has, because we're looking at it for RF, so in other words, this wire can function as a safety ground, but because of the wavelength, this is not a good RF ground anymore, because it now has waves forming on it, and depending on where that wave ends up, starting at the 0 volts end, because it's actually tied to the earth, we are no longer at 0 volts anymore. And this will result in, as I experienced when I was about 17 years old, you lean over to talk and your lip hits the microphone and you get a shock. And it was not because it was 120 volts. It was because it was a bad RF ground, because the wire was too long, which is why it's really important to keep your grounds as short as you can, because RF ground is not equal to safety ground. That is one of the big takeaways of this class, that RF ground is not equal to safety ground.
What about ground in a mobile system?
A mobile system, your wires are typically going to be short enough. Now, are you talking a moving car?
Yeah. A mobile system, car on tires.
Yeah. Okay. So the tires are going to insulate you from ground. So essentially your ground at that point becomes the chassis of the vehicle.
Okay.
And yeah, it's possible that your voltage on the chassis of the vehicle is going to float with some RF. I mean, I would say that it's going to have to, but you are also lucky enough to be sitting in the car. And more than likely, you are going to be either floating or you're going to be at the same voltage as the chassis of the car at all times. So yeah, your car is actually going to radiate. And that's why sometimes, our noise that's generated by your car will get into your antenna. RF noise will get into your radio, and vice versa. There have been stories of people who key the radio and their car shuts off. It hasn't happened in a long time, but it's certainly possible. So, but as far as, like, if you think of it as a safety ground, your connections are typically going to be really short in a car. So that's not an issue. All right, other questions there? Okay, here we go. So 99% of problems that you encounter in electronics, electrical design, etc., come down to an application of Ohm's law. And what is Ohm's law again? Somebody tell me what it is.
V equals IR.
Yep. Okay, so now I'm going to draw a circuit, right? And here is my car battery. And I'm going to draw a resistor. The resistor is actually my wiring. And then I have another resistor, which is my load. So that is what I use. This is what I consider my transmitter to be. So the wiring, ideally, what is the resistance of my wiring? Hopefully.
As close to 0 as possible.
As close to 0 as possible. Exactly. So let's say that this is at 12 volts DC. And my load is going to draw, let's say, 10 amps. I have a 10 amp load. By the way, if anyone is curious, we're on page 55 now. So let us say that here's my wiring right here. This is my vehicle wiring that goes from my car battery to my load. All right, so we draw 10 amps. So that being said, if we are pulling 10 amps and this is a 1 ohm resistance in my wiring, what is, if I were to take a meter and go like this, what voltage will I measure across that? Ohm's law works for batteries. It also works for wires. So this is 10 amps. What does Ohm's law say? E equals I times R, which is 10 times 1, which is
10.
10 volts. Okay. So if I go around a circuit and I start at 0, I'm at plus 12. I lose 10 volts in my wiring. That means at this point I have 2 volts to run my radio. Does anyone see a problem with this?
Yeah, you're not going to run your radio.
You're not going to run your radio very well. In other
No.
words, because that wiring has such a high resistance, there's no way you're going to have enough voltage left to run your radio. So that is why, let's say we go from that to 0.1 volts, or sorry, 0.1 ohms. And then this goes down to a 1 volt drop. And now we have 11 volts to run the radio, which is still not ideal, but it'll probably still work. So how do we achieve a lower and lower resistance in our wiring?
Make the wire thicker.
Make the wire thicker and
Better quality.
what else?
Shorter.
Shorter, yes, because if you look at how wire is built, what it actually is, wire is like a cylinder, right? And DC distributes itself uniformly through the wire cross-sectional area. It's universally distributed throughout. The bigger the wire is, the more cross-sectional area there is, the less room there is for electrons to crash into each other. So this reduces, making a bigger wire reduces your resistance. The other thing, of course, is if you have to go through this distance, you have a certain amount of resistance. And actually wire is resistance per 1,000 feet, usually. That's usually, or resistance per foot, but usually per 1,000 feet. If we double our length, what happens?
Double your resistance.
We get double the resistance. This is exactly what we don't want to do. So let's say that you end up with a cable and let's say you move your cabling from one car to another, and you end up with an extra 25 feet of cable, 25 feet of power cable. So you just go into the back of the car and you do this with it. And you coil it up. What would be a better option?
cut it.
cut it. That's right.
Yeah.
And it goes kind of against what you want to do because, why would I want to cut my cable, right? I can't put it back together very easily. I'd have to put connectors on it. But this is what you would do. You would cut this section out and just go from there to there and cut out your cable because you're basically inducing losses in your power cable. So you want your connectors to be as short and direct and as thick as possible for all your wiring. And that is to avoid voltage drop. Okay, so if let's say you're figuring out what kind of power supply to buy. So we have a radio here that is going to draw 10 amps at 12 volts. By Ohm's law, the other portion of Ohm's law, how much power is this going to need?
120 watts.
Right, because P is equal to I times E, which is 10 times 12 is 120 watts. Okay, so how big of a power supply would we probably get?
More than 120.
That's right. Okay, the reason being that we have power loss in the wire. And on top of that, this is probably only a 50-watt radio. Well, why is it using 120 watts in the first place? What do you think?
Because of the resistance.
No,
No?
So,
It's inefficient.
it's inefficient. That's right. Your conversion of power of electrical power into RF output is not, it's about, depending on the mode you're in, anywhere between 50 and 70% efficient. So that's why you have a heat sink on the back of your radio. And on top of that, does your radio have electronics in it? Does it
Yeah,
have lights?
Yeah.
Does it have a digital display? All right. Even if you're not transmitting, that's still running. So you have to account for that, which is why you actually draw considerably more current than you think you're going to need. And then on top of that, your power supply is not really 100% efficient either. And they're typically rated X amps continuous, Y amps surge. So if you're going to be holding down the microphone and hitting the push to talk button for a while, you really need that X amps continuous to be suitable to run the radio. So for this particular thing, I would assume at least a 12 amp power supply, continuous. The reason being that you're probably going to add something else also. You never know, maybe you want to throw something else in. Maybe you get a new radio that pulls a little more power. So that's why you typically will oversize it a little bit. Okay, so which of the following must be considered to determine the minimum current capacity for a power supply? Efficiency of the transmitter, receiver and control circuit power, and power supply regulation and heat dissipation. Again, efficiency of the power supply. Okay, how can a computer be used as part of a ham station? You can use it for logging software. Pat, you said you've done that.
Mhm.
For sending and receiving Morse code, which we displayed.
What's
Um,
CW? What does that stand for again?
Continuous wave.
Okay.
Continuous wave being that you basically have a wave that's on and off. When you're holding it down, it just stays on the whole time. So it's a continuous wave. You just modulate it by turning it on and off. And for generating and decoding digital signals, which is that software that I showed you, like for instance, FL Digi. Which of the following connections might be used between a voice transceiver and computer? As we discussed, what I'm going to do is, so here is my computer and here's my radio, and we're going to do a simple integration between this. So a radio has a speaker and a microphone. And this would plug into the radio. And also on the side of this microphone is a push to talk switch, which connects to the radio. So here's push to talk, and here's the mic, and here's the speaker. So we basically have to have this computer duplicate exactly what somebody would be doing. So there is a hardwired push to talk line. So here's push to talk. Your computer also has a microphone input. So the speaker of the radio would talk to the microphone input of the computer. And the microphone input would have to get information from the speaker output of the computer. Once you've connected all those things, essentially the computer replaces the person. And you can use that for communicating.
And the advantage is, or is there an advantage?
Oh yeah, the advantage is that you can then use programs on the computer to do digital communications.
What
So
would be an example of digital communications?
You mean sending packetized data?
So let's say I'm going to pop this up on the screen again. And I closed it already, but that's okay. Here we go. Can everybody see that?
Yes.
Okay, so again, this is a free program called FL-Digi, which is it's a digital communications program. And here are the different modes that, because it actually it integrates the sound card and the speaker audio, or the sound card, speaker audio, microphone, and push to talk within your radio. You can configure it for a lot of different equipment. So you've got your, I don't know why it seems to be Italian today. But here's your configuration. And here is your grid control. So basically, this would normally be in English. I don't know why it's in Italian today, but this is basically where you would set up your equipment. Notice there's a sound card right here on COM3, baud rate, the description of the radio. This software actually directly controls the radio that I have in my station using the sound card that's integrated into the equipment. You could also use an external sound card. You can also use a sound card inside the computer and just use the, you just have to add a push to talk line, hardware integrated. But notice all these different modes. So all these are frequency shift keying. If it says SK, so phase shift keying, quadrature phase shift keying, eight phase shift keying. So there's quadrature, which is 4 quadrants. This is 8 separated into 8. Teletype, fax. These are all signals that can be used on the air. There's something called Hellschreiber. FSQ is a very slow text-based mode. And look, it could even do Morse code, CW. So that is how you would use your computer to transmit and receive digital stuff. And in fact, there's a lot of digital going on right now on the air. And that's one of the things that I'm going to be showing you guys today. Okay, let's see. How is a computer sound card used when conducting digital communications? The sound card provides audio to the mic input and converts received audio to digital format. All right, so there's also something called a ferrite choke. Everybody here has seen one of these. You may not know that you have. Everybody has a computer or a power supply for a computer, I assume. You ever seen one of these things on your power supply? Any idea what's in it?
Magnets.
Sort of.
Ferrite.
That's a ferrite. Okay, so what is a ferrite? What actually is a ferrite? So typically what a ferrite is a ferromagnetic material such as iron. So it's not magnetized, but it is magnetizable very easily. So iron is really good for that. There's also nickel and a whole bunch of other metals. You can then alloy them together And typically what you do is you put them into a powdered format and add some glue or binder and make them into the shape of a kind of like a, I guess you'd call it a cylinder, so that you can pass wire through the center. So what's interesting about a ferrite is that, okay, every wire can function as what, everybody?
A magnet.
No, every wire can function as what?
An antenna.
An antenna, that's right. Every wire, if it has current going through it, can function as an antenna. So there's another function of this, which is, okay, let's say that this is your microphone cable, right? And your microphone cable is shielded. So you've got a center cable or center conductor and your shield, and your shield is in theory grounded, right? But that mic cable is actually a little bit long. So it actually could pick up radio frequency interference. The stuff on the inside of the shield is pretty much safe, but the microphone cable shield can actually carry radio frequency interference, which can then get into your radio and mess things up and make you sound all distorted. So the current, the radio frequency current, which is flowing on the outside of this cable, generates a magnetic field. Well, this is a ferrite. The materials in the ferrite are chosen so that at particular frequencies, and there are different mixes based on what you want to do and what frequency you're operating at, different mixes of materials with glue and such, that the magnetic field that's generated is largely spun around and contained inside this material. And this material, because of what it is, tends to suck up the power and get warm. So essentially, you have, as energy is traveling down this way, you have potentially lots of RF on the cable. And over here, you have no RF, which is radio frequency. Essentially, what the ferrite does is it allows you to burn off unwanted radio interference. And that is why we have this thing on our computer power supply. Whoops. That's why we have this thing on our computer power supply, because interference could be traveling down this line, but once it gets past here, it's not going to be carrying anything.
I've seen devices that have, they recommend the ferrite cylinders, but they recommend that you wrap the wire around
Yes.
the ferrite cylinder
Yes.
a couple times.
And some ferrites, actually, it's called a ferrite core, or it's basically the shape of a torus. And a ferrite is also the basis for a lot of transformers because it tends to constrain magnetic fields inside it. So if it constrains magnetic fields inside it, that means that you can actually wrap things around it. You can wrap multiple things around it and use it as a transformer too. The reason that you would take a wire and pass it through the core of the ferrite multiple times is because you get a multiplicative effect, that you get a little bit of attenuation of your signal by going through once. If you go once and then twice and 3 times, 4 times, 5 times, you get a lot of attenuation. So every time you go through, it couples even more of the signal into that ferrite and hopefully burns it off. Nate, you raised your hand.
I was wondering if you should keep the microphone wire short too.
I think that's a good idea.
And
Yeah.
are we using the ham radio license manual right now?
I sent out one of the things I sent out to everybody was a zip file that contains the no nonsense study guide as a PDF. Okay, so
Scott?
Yeah.
I have a cable here that is only used to charge the battery on a camera. Why
Okay.
would they have a ferrite choke on that?
Because it's got a power supply, right?
Well, you plug it in on one side and it
Right.
goes into the battery in the camera.
Okay, so what is
It's
a
a little
power?
point and shoot camera.
Yep. Okay, so let me ask this question. Okay, that power supply that we drew yesterday is called a linear power supply. Most power supplies like this one. Okay, so this power supply is a 200-watt power supply. If this were a power supply that had a transformer in it, like a normal size transformer with a normal size power supply, it would be the size of my laptop computer and
Ah.
weigh about 25 pounds. So how do we achieve being able to get that much power out of such a small device? And that is not a linear power supply. That is called a switching power supply. And the way that a switching power supply works is that you basically generate a voltage and then you use a transistor. And let's see if you can pick up the problem here. You switch the power on and off really fast, like 25 kilohertz, and you generate a square wave output.
So you're creating the RF when you're doing
You
that.
are creating RF
Yeah.
when you do that. And in fact, because it's a square wave, it's particularly ugly and has all those harmonics of that fundamental frequency, which means that it's generating a whole mess of different frequencies. That's a fundamental to a switching power supply in that it allows us to generate massive amounts of power out of a very small package with a very small transformer because the frequency it's operating at is so high.
Hmm.
That's the same reason that aircraft operate their power at 400 hertz instead of 60 hertz, because transformers that would normally be this big are now only this big, and they don't weigh as much. And in an airplane, weight is everything.
Yeah.
So basically, what it allows you to do is operate at really high frequencies, which means that your transformers are very small. And we are on page 56, by the way. So what you achieve by doing that is very small size, but you also generate RF, right? So part of cleaning up that signal is capacitors. The bigger the capacitor, the better the filtering, right? Well, the whole power supply is only this big. So the capacitors that are in here for cleaning it up and flattening everything out and making it nice and clean, they only work so well. And there's still some RF that might sneak through. And you knock that out by DC is unaffected by a ferrite. AC will get swallowed up.
Ah, okay.
It essentially becomes a filter
Okay.
by working on the induced RF. And that's why even a very small power supply will typically have a ferrite choke on it. And then of course, on top of that, it could also pick up energy, but that's also why, from outside, but that's also why typically your ferrite is going to be very close to the power supply itself. The less distance it has to travel along this wire, the less it's also going to radiate and interfere with other things.
So you said the ferrite chokes are only used in AC applications?
They only work on AC. They only work on magnetic fields that switch back and forth.
What's pulse width modulation? How does that relate?
Pulse width modulation is basically just generating square waves, but it changes the duty cycle. In other words, the pulses, literally, it's always the same frequency, but the pulse widths are changed. So to generate more average power, your pulses get longer. In other words, you're on more of the time. To generate very little power, you make your pulses very short. So you'll have, let's say, 10% on, 90% off. That doesn't generate a lot of power, right? Because it's only on 10% of the time. But you could switch it from 90% on and 10% off. So you'd be producing power more of the time. and your overall frequency of your signal stays the same. Does that make sense?
Yeah.
Okay, so that's PWM or pulse width modulation. Okay, let's see. This actually brings up another interesting point. Okay, so I'm going to draw a piece of wire. Okay, so if I were DC current, I would be, my current would be completely distributed through the entire cross section, right? All right, so for DC, my power is, again, distributed completely throughout the cross section. If I am AC, however, my current flows on the surface. And as you go toward the center, there is nothing, there is no current flow in the center, and it is lower and lower the closer you get to the middle. So for AC, power flows on the outside of the conductor, and this is called the skin effect. So if you want to optimize the amount of surface area of a conductor, what would you do with it?
Flatten it out.
Flatten it out. So you would basically pound it completely flat, which is why if you want to do grounding, you would take your conductor and you would use a flat strap, because that gives you the most surface area for current to flow to ground, if you're doing RF grounding. And again, that's known as the skin effect. And actually this even works at 60 hertz power. If you've ever seen a power plant or like a power substation, you may notice that some of the conductors that they use to connect things actually look like pipes, you know, big round pipes, even though it's electrical power. And you think, wow, that's weird. Why wouldn't they just make a solid conductor? The reason being that the power is going to flow, the current's going to flow on the outside of the conductor anyway. So you might as well just make it hollow. Another challenge is noise generated by a car. Oh, let's see, here we go. Sorry, I skipped one. Where should the negative return of a mobile transceiver's power supply be connected, or power connector be connected? And the answer is you want to go all the way back to the battery. Okay, so why is that? Somebody give me an answer based on how cars are built.
Why couldn't you just ground it anywhere on their chassis?
Excellent question. Okay, so here's the question. So let's say that I have my radio back here. That is a great question. So power obviously goes to the plus. So I have the negative terminal of the radio. Why would I not just ground it to anywhere on the chassis?
Oh, because it's acting as an antenna?
That's part of it. But here's the other one.
It's also,
What is the resistance of your car frame? What is the resistance of the chassis? And the answer is, I don't know. I have no idea. Is the frame of the car, let's say this is a 100-watt radio and it's pulling 22 amps. How much voltage loss will there be when you try to pass 22 amps of return current back through the frame of the car? And the answer is, I don't know.
Wouldn't you expect that much metal to be way more than sufficient for?
You'd think
conducting that?
so. You'd think so. But let me ask a question. Was a car built for that?
No.
So did the designers of the car design it so that it was, okay, so you have this piece of the frame and it's spot welded to this piece of the frame, right? What is the quality of that spot weld? I don't know.
I would think also it would, the integrity of your contact points on the frame would probably be a big issue too.
Well,
how well they maintain their conductivity.
And I've done that. And what you do is, if you're going to do that, you have to actually scrape off all the paint.
Right.
And prep it, and then make your connection, and then coat it with an anti-rust compound.
Right.
But yeah, I mean, the question is, what the car really, the frame, yeah, it'll probably work, but it really wasn't designed for that. And you don't know how good of a job on spot welding for being RF resistance. You don't know what the resistance of that spot weld is. It's kind of hard to say unless you go test it. The easier and less stressful way of doing it is to just make your connection using the same gauge of wire that you used to run your power to it, directly back to the battery.
Can I back you up just a little bit on
Yeah.
the strap? You said the strap is used for AC grounding?
Yes.
Okay, so why do a lot of cars use a strap for grounding the alternator to the chassis?
Because it's easy to work with.
Okay,
You can take a strap and you can just put a hole in it and just bolt it in place because it's flat
yeah.
And it's usually braided, so
and
it's
it's
not gonna have
really
metal
flexible.
fatigue.
Yeah, it's really flexible too.
I have a question.
Yeah,
I
Don't
got a-
alternators also create a lot of RF?
they can make some RF. Typically what it ends up doing is making a whine that you can hear coming in through the power leads. So your power can have a superimposed whine on it, which can come out in your audio. Yeah, go ahead, Pat.
I got a question, and this is basically older vehicles that it's just the alternator that could be causing it. I hear that newer cars you have a much harder time distinguishing what the noise is from.
Because you have
Any insight there?
because you have an engine control module and you have a lot of things that are electronically run. Yeah, it is.
Any workarounds on that? Because I have
Not
a
really.
vehicle like that.
Not really.
Okay.
I know that when my car is when I first start it, I get a whine coming out of it. And I know that has to do with the engine control module starting up. Just
Okay.
It just is.
Okay.
Another thing that can happen. Okay, so you get a whine that varies with engine speed. That's the alternator. Sometimes you can also get a pulse noise, pop, 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 which varies with speed, and that's usually due to the spark plugs firing. And so that's to remove ignition noise. And to remove a periodic noise like that, you would use something called a noise blanker. And that would reduce ignition noise. Ignition noise is very distinctive. And actually, when I built my mobile station, I actually went and bought $100 set of spark plug wires, which were specifically designed for RF suppression. And they work great.
Monster?
No, they weren't. It was specifically, the wires themselves. The wires themselves were qualified to run spark plugs, but the material that they were built in was actually built with was actually RF suppressing.
Could you go back to the noise blanker? That
Mhm.
sounds like something you'd buy at late night TV in the 70s or something.
It's built into the radio. Every radio's got one.
What?
Well, every
What's the theory on it?
noise blanker, it basically, it's typically in the IF chain, in the intermediate frequency mixers, and it senses a periodic pulsing rising
Noise
of the signal coming in, and it essentially lowers the gain of the receiver during that time. I mean, it's also possible to sense what's coming in and generate an opposite signal and add it to it.
Mhm.
But that's a little bit more complicated. All right, so we are into operating controls, tuning, use of filters, squelch function, AGC, repeater offset. Before we go into that, I'm going to do another quick thing here. All right, so let's say that I have this circuit. And I have my in and I have my out. So my signal is going this way. Okay, and this signal contains DC and AC, both. So let's say that if I were to draw this signal, it would look like this. So here's my 0 volts. So basically what we're looking at here is here's our bias. This is what would be known as the DC bias, which raises the sine wave, and this would be my sine wave. So it's essentially a sine wave that's been shifted from a normal position. So that can be viewed as a sine wave plus DC. So what do we know about capacitors? Remember what we said about capacitors? AC goes through a capacitor really easily, and DC gets blocked. An inductor, DC, goes through an inductor very easily, and AC gets blocked. So what do we have here? What comes out? Everybody, what comes out?
Just DC.
Just DC. The AC gets shifted down and thrown out to ground. So is DC high or low frequency?
Low.
Low frequency. This would be called a low pass filter. Okay, so now what I'm going to do is I'm going to reverse the way this is built. And I'm now going to draw this with a capacitor here and an inductor here. So the DC is now going to go this way, and the AC is now going to go this way. So now what's going to come out at the end?
High frequency AC.
High frequency. That's an AC. So is AC compared to DC high or low frequency?
Hi.
That would be a high pass filter. Okay. So now what if I got creative and I picked my component values that went like this, and then I coupled this, because remember, it's not 100% perfect, with this. And I picked my component values carefully so that I were to split this. Right here, I would have a low pass, and then, whoops. And then this would be coupled with a high pass. If I were to draw these frequency responses, I'd have a low pass that maybe looked like this. At some point, there's a little bit of it actually rolls off. It's not perfectly square. But then my high pass looks like this. And this goes from frequency of 0 to infinity. Well, so what am I left with? I'm left with this intersection right here.
Notch filter.
That would actually be called a band pass because it allows just the band to go through. Now I could also
But where in your circuit are you, where do you get that output in your circuit?
right at the output. So here's my in and here's my out. So this end result is what would come out of the end because I've basically cascaded a low pass and a high pass section, and my end result is a band pass. And that is because the low pass does not just allow only DC, it works better at low frequencies based on the components that I pick. And the high pass works better based on the components that I pick at certain frequencies. I could actually make this, I could pick my components so that my picture actually instead looked like this. There's my low pass and there's my high pass. What would I get out?
Nothing.
Nothing.
Nothing. I'd get nothing at all.
Does it matter which one is first?
No, it does not. They're cascading in that regard. So here's the next question. If I were to take and choose my components so that I ended up with something that looked like this, oops, hold on, let me draw that again. What would that be?
Still not getting anything.
Well, you are actually, if I were to put these in parallel, for instance, instead of in series, if this was my overall frequency response at the end, what's cut out of it?
A notch.
A notch, and that would be called a notch because there's a notch cut out of it. So essentially, if I take a bandpass filter and I invert what it's doing, this is called a notch filter, also known as a band reject filter, because it's rejecting a certain band of frequencies. And all these are done with capacitors and inductors. So remember I said capacitors and inductors are the cool part of radio? And that's why, because they're the basis of developing filters. So you actually already have in your life, I guarantee, this exact same thing, and you probably just don't know it yet. So let's say that you have a speaker system, and it's a three-way speaker system. Most speakers, like in a car, are not just one speaker. You have a small speaker. What's the small one known as?
Tweeter,
A tweeter. What's the middle one known as?
mid-range,
And the big one?
woof
Okay.
woof.
Okay, so here's the question. What is the frequency response of a tweeter?
High frequencies.
Very high frequency. How about the mid-range? Obviously,
Mid-range,
middle. And the woofer?
low.
Okay, so what would be the point? Let's say that your signal contained everything from 0 to 20,000 hertz. This little speaker was good from 10 to 20,000 hertz. And this middle was good from 3,000 to 10,000. And the bottom one was good from 0 to 3. What would be the point in sending the high frequencies down to the big woofer? What would be the point? And the answer is there is no point. So if you've ever seen something called a crossover network, this is a low pass filter. The high frequency, the tweeter, gets a high pass filter, and the mid range gets a band pass filter. And if I were to draw the signals that are going to it, I would see here's the incoming signal, frequency from 0 to 20,000 hertz. The low pass filter, it would get something that looked like this coming through. The high pass filter would get something that looked like this coming through. And the band pass filter would get all the stuff in the middle. And I would design my circuitry to do just that. And that is exactly what's in your crossover network. So that is the point of filtering. That's why we do filtering. So
Is this
now,
Is this also what would show up if you were to try to mitigate noise induced in somebody else's equipment? Let's say you were creating a interference on someone else's telephone or whatever.
exactly right. Okay, so what we're going to do is bring this up. Here we go. And okay. So what we're listening to here is an SDR, a software defined receiver, that is in the Netherlands. And what we're going to do is zoom in on this. Okay, so does everybody see this little yellow thing right under the number 14043?
Yes.
This is actually a filter. And I want to note, I want to show you what happens when you stretch out the filter limits. Notice we can hear more things and we get higher frequencies. I can do the same thing here. So what kind of filter are we listening to right now?
Bandpass.
That would be a bandpass filter. I could turn this into a low pass, just a plain old low pass, by doing this with it. Notice what we're listening to. What frequencies? Just super low. I could also make this a high pass filter. What are we getting to listen to, everybody?
Tweety bird.
Yep, that's just the very high frequencies. So basically what we're able to do, this is all digital as opposed to physical filters using inductors and capacitors, but it's a really good way of showing exactly how a filter works. So now we're also going to look at filter bandwidths. We're going to change to phone, which is voice, and we're going to keep that. We're going to find a voice signal, and we're going to go to upper sideband.
Do we have any last minute check-ins for the Air Force Flyers Club net members or visitors? Please come now.
Okay, so remember we said that a voice signal is about 3,000 hertz wide. Well, there we go, from 14.290 to 14.293. That's about 3,000 hertz. This is single sideband. Now, what we're going to do is intentionally mess things up. And tell me how much you can understand if I knock it down to 500 hertz. How much can you understand?
Nothing.
And why?
Okay, whiskey.
Why is it that we can't understand it?
We're only hearing parts of the tones.
That's right.
The
You're
words,
only
tones.
getting some of the information that you really need to understand everything. So if your filter is not matched properly to the mode that you're operating, you won't be able to copy it. You won't be able to understand it. So essentially, like you said, what we're doing is we're missing a part of the information. We're missing a part of the signal. Here's another one.
Again, this is Kilo Quebec is Zero Lima. The name is Leonard of the Mile High City, Denver, Colorado.
So let's switch it to the wrong sideband. Now we're listening to lower sideband. Why can't we understand this? Why can't we understand that?
They didn't put any energy into the signal.
Well, I mean, we're still listening to the signal, but we're expecting it to be down here. We're listening to the wrong sideband. We're actually inverting the audio. It's actually completely wrong. So things that are supposed to be low frequencies are high and vice versa.
Larry was booming in here, and man.
We can also Donald Duck this guy.
So when you're listening to the wrong sideband, you should be able to mirror it.
Well, you won't be able to hear it. I mean, basically, the way to fix it is to switch to the other sideband, because you won't be able to understand any of it. I mean, in theory, yes, you could, but.
Yeah, okay.
Okay, so what can happen if your microphone gain is, okay, we're on page 58. If your microphone gain is too high, you'll sound distorted. Basically, you're pushing your transmitter too hard. What can be used to set an operating frequency on a transceiver? That would be a tuning knob. You also very frequently, essentially this is our tuning knob on this receiver.
So wait a minute. So you're saying tuning knob in English, and the answer says VFO.
Yeah.
So if we get this question and we look for tuning knob, me being a small brain mammal is going to go, I don't see it.
Okay, so it's a VFO, which is a variable frequency oscillator. So the variable frequency oscillator is for tuning.
It's all a that's all the tuning indicator is. Anyway, you're always varying the oscillator of whatever you want to listen to.
Yeah, so let's bring up ICOM IC 730. Okay, so this is a classic radio. Like, we're gonna bring up this picture of this vintage ICOM 730. Okay, so notice we have a display. Notice here it says right in the middle, dual VFO system. So a VFO is a variable frequency oscillator that determines what frequency you're operating on. The tuning knob is used to adjust what that is set to. On the left, you've also got something that says memo, which is memory locations. So very often you'll have memory locations in a radio as well to allow you to bookmark individual frequencies. And in this particular case, notice there's a little button that says A, B that allows you to switch from VFO A to VFO B. It basically, for quick reference, it stores two different values. So on an older radio, because this is all synthesized, the frequency is actually generated by a microprocessor, that being synthesized. On an older radio, for instance, let's say on a Collins S line, for instance. Let's hope we can zoom in on this one. There we go. You notice what your tuning mechanism for your VFO actually is. Right, you notice you actually have a numbered display inside that little window. And when you spin the knob, it actually physically moves a capacitor or an inductor, depending on how the tuning circuit is built. So therein lies a little bit of an issue, because as things get old, capacitors and inductors and stuff like that, they tend to drift. They tend to not be exactly as they were manufactured, which means that the frequency that you're tuned to and showing on the display might actually be a little bit different. It's typically not going to happen with microprocessor controlled radios, but it will happen with older radios with actual physical components for setting the frequency. So which of the following can be used to enter the operating frequency on a modern transceiver? It would be the keypad or VFO knob. Again, VFO is variable frequency oscillator. Let's see, on other radios, I'll actually have a keypad for just punching in a number directly. In order to enable quick access to a favorite frequency on your transceiver, you'll have a memory channel. You can just punch in the memory channel and it'll bring it up. Which of the following is a use for the scanning function of an FM transceiver? This radio right here that I'm holding up has something like 250 memories in it that you can program, and you can actually hook it up to a computer and dump the computer program in containing all the memories that you want to scan, and just hit the up arrow, push and hold it, and it will scan all those memories. This radio actually has, I believe, 200,000 memories that it can scan. So it has a lot of memory channels that you can program.
What radio is that?
This is an Anytone 878 DMR radio, digital mobile radio. It also does analog, but it's what is it, 878 UV plus, I think. I picked it up on closeout. Let's see, a common receiver control is the squelch control. Okay, so I'm going to demonstrate squelch right now. Here we go. This is squelch. Okay, that is my squelch not activated. Everyone hear that annoying sound? What we call static. I'm going to turn the squelch on. Much better, right? Okay, so what is squelch? The squelch circuit mutes the receiver output when there's no signal to be listened to. So basically, if there's nothing to be heard, it turns off the receiver sound, so it doesn't annoy you. Now, there are times, let's say that you're trying to hear a weak signal that you don't want the squelch off. You actually want to hear that signal that's just barely at the noise level. For the most part, if you're listening to a repeater and it's a strong repeater or a strong nearby station, the squelch will basically save your ears from having to hear all that static. And in my case, having your wife complain, will you please shut that damn thing off? Yeah.
Question or
Yeah.
comment. I've had people on, when I've been at NCS, actually turn the squelch way down so they can't hear anything. And they're texting me going, I can't hear the net.
Yeah.
So you can turn it way down too much so that you don't even realize that you're missing out.
Actually, we run a weekly simplex net here on Saturdays. And on simplex, you get signals that are not going to be as strong as a repeater. And we actually say the net control station and all the relaying stations will actually say, hey, everybody, turn your squelch off. Tell us what you can actually hear, because for instance, there might be a station that is, because we're operating simplex, there's no repeater involved, down in a valley or 50 miles away on a handheld, and you can actually hear them if you turn the squelch off. So
Wow.
yeah, we do that every week as practice. It's a lot of fun, actually. Okay, let's see. So next, what is meant by repeater offset? Okay, so for this, we're going to do our first drawing of a repeater station. Repeaters are now ubiquitous throughout radio, all forms of radio. Okay, so if I am transmitting, if I have person 1 and person 2 transmitting on the same frequency, going back and forth on the same frequency, let's say 146.52 megahertz, which is the national simplex calling frequency for 2 meters. This is a very important frequency to remember. This would be known as simplex. Only one person can talk at a time, and you're using the exact same frequency. So that would be known as simplex. Okay, so now what we're going to do is we're going to have these different stations talking on different frequencies. Frequency A and frequency B. All right, so in order to do that, station 1 would be transmitting on frequency A, and station 2 would be listening on frequency A. Station B would be transmitting on frequency B, and station 1 would be listening on frequency B. They are different frequencies. The difference in frequency would be known as an offset, so that when you keyed your transmitter, it would automatically shift the frequency to the frequency that you wanted to be transmitting on. That is known as a frequency offset, or in case of a repeater, there's a repeater offset. The reason that we use a repeater offset now is because we're going to redraw this. So here's me, and we'll just say you, and here is the repeater. A repeater is an automatic station that always listens on one frequency and always retransmit on another frequency. So this repeater would be listening on 146.12 megahertz. And in order to get heard, what frequency would I have to transmit on to get heard? Everybody?
14612.
14612, which means that my transmitter would have to be operating on 14612. How about this other frequency? This other station over here. What would it have to be transmitting on?
14612.
146.12. So every station that was involved in trying to use that repeater would have to be transmitting on that same frequency, hopefully not at the same time. This repeater station sends a signal out to the world, to everybody, on 146.72. This is the published transmit frequency of the repeater. If I am listening, what frequency will both of us have to be listening to in order to hear it?
146.72.
146.72 receive.
Mhm.
So what that means is that I would actually have to program my radio to receive on this, as would everybody else, And we would have to transmit on a different frequency. And notice, what is the difference between those two frequencies? We're just going to do some math. 146.72 minus 146.12.
0.6.
And it's 0.6. And is it a positive shift or a negative shift? From there to there. We switched from 14672 to 14612.
Oh, it's negative.
It's a negative shift. So this is the size of the shift. And that's 0.6 megahertz. And we can also say 600 kilohertz, negative shift. So that when you actually go and try to get into a repeater, what you will find is that I'm going to open up something called Repeater Book. And yes, and Repeater Book. Okay. Incredibly good resource. This is another free resource. You may have noticed a common theme here.
What is the, what's the logic behind the size of the offset, the magnitude of the shift?
It is just by convention.
So it's not to handle, to be certain to be able to handle all bandwidths that are likely to come through?
Well, I mean, what did we say was the bandwidth of an FM signal? Because these are all FM. What is the approximate bandwidth of an FM signal?
10 to 15
kilohertz. That's right.
kilohertz.
And the shift is 600 kilohertz. So
It's half
that's
of
not
that.
an issue. What comes into play is, and I will show you this as well. Let me bring up North American repeaters and we'll go to Oregon. We'll go to my repeater. Go to all repeaters on 2 meters. This is a great resource. Okay, so 146.72. There is our repeater. Junction City, Prairie Peak. Okay, open echo link. Okay, notice what this says. Negative 0.6 megahertz. So our published frequency is 146.72 megahertz. Our offset is negative 600 kilohertz or negative 0.6 megahertz, which means you will have to transmit 600 kilohertz lower to get heard. Now, here's the other thing. This thing that says 100.0, this is a continuous tone squelch system. And the way this works is that because it was actually developed by Motorola in the 1970s. Because there are certain areas where repeater frequencies are shared, and actually simplex frequencies are shared as well. This is a very low frequency tone. So this is 100 hertz in this case, that is transmitted at the same time as your voice, which if it is heard by the receiving station at the repeater, it allows the repeater to retransmit. If it's not heard, it keeps the repeater quiet. And that's known as CTCSS or private line or PL.
Right, so you're saying that you have to transmit your communications on that tone, so
Correct.
that way it'll hear the tone and then in essence filter that out and send what you're sending out.
Exactly right. And the reason that came about was because of Southern California. Let's say the LA basin is such that there are, 8 million people, 10 million people living there, and a lot of radio systems and a lot of reuse of frequencies. There might be 5 repeaters on the exact same frequency. So
then when so that means that you need to pick, okay, so where I am, I know that there's a repeater at the end of the valley. And if I want to hit that repeater, I go to this book and I find out what the stuff is. I have to set my frequency and my offset. And then I also have to induce this other tone.
Yes. And
that's common on all radios, right?
Every radio has that.
Okay.
Yes. Yeah. And that's the CTCSS. Now there's also another thing called a DCS or digital coded squelch. And if we go to 145.13, you'll see this DCS, it says D023. It's similar, except that it's a continuously sent series of low frequency tones in a pattern. So it looks for that and uses that to open the squelch. So very similar, but a little bit different, but they serve the same function. So that's again, CTCSS or DCS. All right, notice this also is tied to something called Echolink. Echolink is a means by which you can actually connect a repeater or another station to the internet. And what's cool about Echolink is that there's an iPhone app for it, which means that if you're a licensed ham, you can apply for, you can send them all your information regarding Echolink, verify that you're licensed. They set you up with an account, and basically you can then get on the radio from anywhere that you have an internet connection if there's a repeater that has Echolink. So I'll go back down to 14672 and notice we say FM Echolink. Well, that's pretty cool because, for instance, my our club vice president has family in Costa Rica. He was visiting them and he was able to get into and participate in our nets from Costa Rica because he had internet access there. Okay. So let's see. So that's repeater offset. RIT is receiver incremental tuning. Essentially, receiver incremental tuning is something that you don't really use on FM. You do use it on single sideband or on Morse code. And what it allows you to do is slightly change the receiver frequency without changing the transmitter frequency. And the reason that you would want to do that is because let's say that you are talking to somebody who is using a radio that is something like one of these, where the frequency on the display does not exactly match the actual frequency they're running. It's also possible that they're operating with a station like this down here, where your receiver and your transmitter actually have different VFOs and they might not be matched, in which case their transmit frequency and receive frequency might not be exactly the same. So in order to separate those two frequencies into two different frequencies, you would use something called the RIT, which is receiver incremental tuner, or clarifier. Clarifier is specifically a Yaesu term. Yaesu is another one of the companies that makes a lot of equipment. Automatic gain control, or AGC, we're on the bottom of page 59, is AGC is a leveling control on your received audio, which keeps the received audio constant. If you're using a radio that doesn't have AGC and somebody really loud comes by, it will really hurt your ears. Multiple receive bandwidth choices. We actually just displayed that on this software-defined radio. The reason for having this is that you can knock out noise adjacent to narrow signals. You can also make sure that you can actually hear the entire signal that you're listening to, such as this. Again, if I chose the wrong, receive frequency, it wouldn't work.
Checking in with us, and so anytime you hear us in there,
and again, if I went over to Morse code, let's say it was a really crowded band, I wanted to knock out everything around. Notice I hear a lot of different things here. Can everybody hear this okay?
Mhm.
Let's say I just wanted to filter down and give my ears a little easier day. Essentially, I'm tailoring my filter to make it easier to hear and knock out the adjacent noise. For Morse code, 500 Hertz is a really good filter bandwidth. And actually, you'll see that this is about 500 Hertz wide. For single sideband, an appropriate filter is about 2400 Hertz. Push to talk button, PTT, that's basically a button that allows you to transmit between receive and transmit. On this radio, it's right here on the side. That. It's right here on the side. This is my push to talk button. On a base station radio, your push to talk button could be a foot switch on the floor connected to your microphone. It could also be just on a hand microphone. It could be just the little trigger. All right, so we're up to station equipment. And, okay, yeah.
Is there anything you can add to what the bandwidths are and why for the different frequencies? Is there anything like it's some percentage of it, or it's I mean, are there any rules of thumb that is make
Not
it
really.
not just memorize?
Not really.
It's just memorized.
I mean, CW, well, a CW signal is typically going to be 150 hertz wide. 500 hertz is enough that it allows you, I mean, you can run, you can listen to Morse code with a 100 hertz wide filter. What that does is it basically makes it really hard to tune anything else in, because you're looking through such a narrow little filter. So as you tune up and down the dial, it will be very hard to find another station. You have to tune really slowly. 500 hertz is usually wide enough that you can still tune around and hear stuff.
Can you go back and explain where single sideband lives again and why we need to know that?
Yeah, single sideband is used, and actually let's go and share this right here if I can find it again. I'm sure I can. Let's see, open location. Come on. Okay, so sorry, I gotta find the right thing. Band plan. Okay, so suffice it to say that single sideband, every single, there we go. Band plan. Okay, here we go. So every single amateur radio band has a spot for single sideband. Because single sideband is a much narrower bandwidth, FM has some nasty habits. For instance, if there are two signals, the weaker one always loses. You won't hear the weaker one. If there are two signals and they're of equal strength, they both lose. This is known as the capture effect. And it is essentially a function of how FM works. There's no way around it. Single sideband is used for weak signal work. So you notice this little light green section on each one of these bands, like between 432 and 433, between 221.1 and 221.25, 144.1 to 0.3. This has no FM, SSB, and weak signal work. And essentially the reason that exists is because those bands are there's room for experimentation. Most of the bands are used for FM. But you do have the ability to run weak signal and single sideband modes. You can do digital, you can run Morse code, because a lot of these bands are also used for like experimentation as far as like moon bounce and things like that. And you would almost never use FM for moon bounce because of a lack of efficiency. And that's why you have access to single sideband. So that's where it typically lives on the VHF bands. Now, if we were to look at the HF bands, single sideband is the dominant voice mode. So anywhere that you see the yellow or the orange or the blue, those are all single sideband. And that is because it has there's simply, it's impractical to run a wider mode, a wider bandwidth mode than single sideband, just for saving frequency space. Does that answer the question?
No, it just defines that there's this area that's for weak signal work. I just thought there was something more specific associated with it. I'm trying to understand why. It just looks like, hey, we just set this aside for this, and that's what it is, right?
That's exactly right.
Okay.
To make sure that to make sure that it's still going to be usable, because it's still for experimentation. You know, it definitely has its application. So I would like to just point out while we're looking at this, oh shoot, where is it?
Nate has his hand up.
Nate, go ahead.
What is a single sideband? Like, what's the definition?
Okay, so if I were to draw AM, all right, so this requires looking at our frequency chart from 0 to infinity hertz. And here's our center frequency of our signal. As we generate AM, or amplitude modulation, we generate a lower sideband and an upper sideband. So those are our two sidebands, and they're actually mirror images of each other. They look exactly the same. They just are mirrored. And because they're mirrored, they have all the same information, which makes them kind of wasteful. What's the point of sending something twice if you could just send it once? So in our transmitter, we basically pick to knock out one of them before we ever amplify it. And this has no information at all. So then we end up sending just this part, which is the upper sideband. Or we can do the other one and just transmit the lower sideband. But you have to make sure when you're receiving it that you're on the right frequency and you've picked the right sideband to be listening to. Because if you haven't, then it won't work. Okay. Let's see, where was I going with that? I'll have to find that other thing that I was talking about. Okay, so we are on to what is a transceiver. A transceiver is a combination of the word transmitter and receiver. Transmitter and receiver used to be in separate boxes. Now they're all in one box, known as a transceiver. What device converts the RF input and output of a transceiver to another band? That would be a transverter. The heart of a transverter is something called a mixer. All right, so a mixer, we're going to have frequency in, and we're going to have another frequency in. We're going to call that A in and call that B in, and this is called a mixer. Okay, and now we have our output. So what we end up coming out is, here's our frequency A and frequency B. We end up with frequency A and frequency B and frequency A plus frequency B and frequency A minus frequency B and frequency B minus frequency A and 2 times frequency A and 2 times frequency B, and so on and so forth. There's a million different combinations. It's really dirty. All the stuff that comes out of that is really ugly looking. So how do you think we would pick just this one? What would we use to pick just that one? Starts with the letter F.
Filter.
F-A-S-C?
We would use a filter. We would use a filter that was tuned for just those frequencies, or just that one frequency, which is the sum of the two. So this is known as a transverter. A transverter works that way. And it also works in the opposite direction, where you have frequency going back out. So it works in both directions. And that allows you to take the signals from one band and shift them to another band, and vice versa. A device that increases the low power output from a handheld transceiver is called an RF power amplifier. The reason that there is something called an SSB/CW FM switch on a VHF power amplifier. So we talked a little bit about transistors, and a transistor, again, looks like this. And the problem is that this is what right here. This is a, does everybody remember what that is? That is a diode. What do you have to do to a diode to make it work?
Send current in the right
You
direction.
have to send current in the right direction. You have to basically turn it on, which means that you have to put some current into it to get a copy out. Well, as it turns out, if I had a graph that showed, I keep doing that, current in and current out, at some point, it would go like this and be an essentially straight line. But at some point after that, it would kind of flatten out. So if I want a good replica of something coming in versus something going out, I would pick that it would operate in this range where basically it looks kind of like a straight line. And this is what a transistor actually functions like. This is known as the linear range of the transistor, which means that basically here would be my neutral point, and I would switch it up and down. And anything that went lower would cause this to go lower, and anything that went higher would cause this to go higher. Well, as it turns out, FM doesn't care, but single sideband does care, because what if I were to operate this amplifier like up in this range, what would that cause? Because it's not linear anymore. What's the word for that? It starts with the letter D. That would cause distortion, and it would sound terrible. So I try to avoid that. But for FM, I don't care, because FM is actually just changing the frequency. It doesn't matter how big or small the signal is, if it's plus or minus 20%. Doesn't make any difference. So there is a switch on your amplifier which allows you to switch from SSB and CW to FM. That actually changes how the amplifier works. It changes the bias position of the amp. If it's on FM, that's typically going to be more efficient, because we don't care how it sounds, because it's going to get cleaned up at the other end. If we're on single sideband, it does make a very big difference, because if it's not set properly, you'll be all distorted. This is the same reason why, for those of you, does anyone play the guitar? There's always seems to be one person who plays the guitar.
Just the air guitar.
Just the air guitar, okay. Well, there are some people who are diehard Class A tube amplifier people. And that's the reason why they're Class A tube amplifier people, because it's inefficient, but it's really clean. The way that the amplifier is built and the way it's functioning determines how good you sound. Okay, so set the amplifier for proper operation in the selected mode. Which term describes the ability of a receiver to protect the presence of a signal? Okay, who here can whisper? Give me a whisper. But you're muted. You have to be unmuted. Still unmuted, still muted.
Who's muted?
Okay. We heard somebody. Did somebody whispered, right? Okay, did everybody hear it? Okay. Anyway, that is called sensitivity. That's the sensitivity of your ears to pick up a weak signal, right? Some people whose hearing might not be as good as others, their sensitivity might not work as well. All right, now ready? I want everybody, we're going to do an experiment. I want everybody to unmute right now. Okay. All right, and on the count of 3, I want you to say your name. Ready? 1,
Dan.
2, what? I didn't get there yet. 1, 2, 3.
Homer Turnbuckle.
Okay, so if I managed to pick out one, I heard Homer, right? That would be my ability to select a particular signal. So the ability of a receiver to be selective is its ability to pick up one, to be able to discriminate between individual signals. That's selectivity. So that's sensitivity and selectivity. All right, so who was Homer there?
That was me.
Huge Homer. Huge Simpsons fan here. So yeah, thank you. All right. Okay, we are on page 61, and as when we finish this, we're going to take a break. So, okay, let's see. An RF preamplifier. So for those of you who have some experience with cable TV, you'll understand this. Basically, let's say that we have an antenna up here, and we have a signal the cable that comes all the way down to our receiver. Our receiver has the ability to hear signals that are minus 120 dBm in amplitude. There's a signal coming into this antenna that is minus 126 dBm. Well, we have a decent antenna that adds 10 decibels. It has 10 decibels of gain, and it's pointed at the source of that signal. And we have a cable that has 6 dB of loss. Okay, so let's add this all up and see if we get above that minus 120 threshold. Minus 126 plus 10 minus 6. I get minus 122. Does everyone agree with that?
No.
Yeah.
Should be minus 122. So if it's minus 122, guess what happens? It is below the threshold at which we can hear this. Does everyone agree with that?
Yes.
Okay. Now, what we're going to do is we're going to try to buck this up. And we're going to add a preamplifier. And the preamplifier has a gain that would be a plus 5 dB. The preamplifier also has a sensitivity of minus 120 dBm. Okay, so we are going to take this preamplifier and we're going to stick it right here. Well, okay, so let's do our math again. We're going to go down through the antenna, through the cable, and how loud is the signal that gets down to the preamplifier? Well, guess what? It's still minus 122. What will the preamplifier actually do? Because it's below its ability to hear anything.
Nothing.
Nothing. That will be a useless device. So what we're going to do instead is we're going to take our preamplifier, we're going to relocate it. We're going to put it way up here at the antenna before we lose anything in the cable. Okay, so it still has a threshold of minus 120 dBm. Okay, so what signal is right here? We have minus 126 plus 10 is minus 116. Are we good or are we not good? There's our threshold. Here's what's actually coming in.
We're above the threshold.
We're above the threshold. And now we are at negative 116, and we can successfully add 5 to it. So now we're at negative 111 right here. We take another 6 dB off, and at the receiver, we are now at negative 117. And guess what? By installing a preamplifier all the way up by the antenna at the source where the signal was loud in the first place, we're now able to receive it all the way down at our station, which is why it's important to put a preamplifier as close to the antenna as possible. Okay, next, what is used to convert a radio frequency signal from one frequency to another? That is known as a mixer. The name of a circuit that generates a signal at a specific frequency is an oscillator. That can be a mechanical oscillator, right? Or it can be an electrical oscillator. For RF, it would typically be an electrical oscillator, although not necessarily, because you can actually also use a crystal. A crystal, like a quartz crystal, will vibrate at a very, very high frequency when struck with mechanical energy. To transmit a voice signal, we have to combine an audio frequency signal from the microphone with an RF carrier. The act of putting information onto an RF signal is known as modulation. So we modulate a signal with some other signal, and that puts information on it. All right, so 5-minute break, everyone.
Sounds good.
All right. Think of some questions. Mr. Date, have you figured out your audio thing? Nope.
Who are you talking to?
I was asking Nate if he figured out his
Oh, Nate,
audio.
okay.
The space button wasn't working. Now it's starting to work. I don't know why.
Yeah. I've never been a fan of the space bar.
I just found it out. I hardly do Zoom. Since I just kind of played around and found it out.
Yeah.
But now it's working.
I just found out I can have multiple whiteboards at a time.
Really?
Yeah, really.
I hardly do Zoom like this.
Yeah, whiteboards are awesome to have. All right, everybody ready to keep going? Woohoo. I really shouldn't be this awake. This must be some seriously strong coffee I made. Okay, here we go. We are on page 62. All right, here we go. Which of the following can cause radio frequency interference? Fundamental overload. That basically just means your receiver is getting swamped with energy from everywhere. That would be known as fundamental overload. Harmonics, that would be signals from, let's say that a harmonic is a multiple of the frequency you're operating on. So let's say you're operating on 10 megahertz. That would mean that you're making energy as well on 20 and 30 and 40 and 50 and 60 and 70 megahertz. They would typically get smaller in amplitude as you go up, but they do still exist. One of the reasons that we have to take a class is because we are allowed to build our own stuff. Since we're allowed to build our own stuff, even if you're not going to, we still have to take a class and understand what all this stuff means. We have to meet, if we build our own equipment, spectral purity requirements, just like commercial manufacturers do. So if we build a piece of HF gear, we have to understand what it means when the rules say that all out of band signals must be at least 60 decibels below the fundamental. We know that 60 decibels is a factor of 1 million times. So that means if you transmit with 1 watt on your transmitter, your stuff that's outside the band is legally permitted in this case. So let's say transmit with 1 millionth of a watt. That's why we have to know the math. That's why we have to be able to understand and interpret the rules, because we are given extraordinary powers to design and build our own stuff and actually put it on the air. The worst thing that can happen is if you do something like that and you start interfering with, let's say, air traffic control. That would be a really bad thing. So that's why we have to be able to understand all of this stuff. You know, we're essentially given the same rights to put equipment on the air as a major manufacturer is. Spurious emissions, that is a transmitted signal that is not on any particular frequency that we had ever planned on. So let's say we have a 10 megahertz transmitter and it's putting out a signal on 28.2 megahertz or 68.4 megahertz, and we don't have any idea why. It's just some weird thing that's happening in the transmitter. We have to understand that's called a spurious emission, and it has to not be there. Okay, any of these can cause interference to a TV set or radio or computer speakers. Let's say your neighbor tells you that you're interfering with the radio or TV. What should you do? First of all, you make sure that your own station is functioning properly, and then you don't have any interference on anything that you have when tuned to the same channel. So the first thing you do is make sure, using essentially a control, that all your stuff is working right. And then, because we typically want to remain neighborly and in the good graces of our neighbor, we might actually offer to help them out. The first thing to do is, if you have, let's say you're interfering with a TV, like a cable TV. Cable TV is a closed system. Those connectors tend to have a way of loosening up, make sure they're all nice and snug. What would cause broadcast AM or FM radio to receive an amateur radio signal unintentionally? Well, basically that would be known as fundamental overload. The receiver is basically not designed to handle signals that loud from anywhere. on any frequency. So one simple application of this was I used to live in the Washington, D.C. area, and a couple miles from my parents' house was a radio station which was right alongside the road. And when I drove by, it didn't matter what frequency I was tuned to. That's what I heard. It was a 20,000 watt transmitting station. So if its signals were, let's say, 50 decibels down, that would still be transmitting at about 0.2 of a watt. Well, I'm right across the street from it. I can still hear it on every frequency, and they're perfectly legal to do so, but you know, I'm right across the street. So my radio is unable to reject strong signals from outside the band. So what would you use to block the frequencies that you don't want to hear? What do you think? What kind of device would you use?
Filters.
A filter, that's right. Capacitors and inductors. You would use filters to block the frequencies that you don't want getting in. So which of the following can reduce overload to a VHF transceiver from a nearby FM broadcast station? You would basically, in line with it, put a band reject filter. FM radio is between 88 and 108 megahertz. Our 2-meter band, if you look at the frequency chart, is 144 to 148. So essentially what you have is a band reject filter or a notch filter that would essentially block everything from, let's say, 80 to 110 megahertz and become an impediment. It would have very high impedance to those frequencies. And since you're not operating on those frequencies normally, it's not a problem. It used to be that, has anyone ever had a wired telephone in their house from the phone company? Okay, so we used to rent those telephones, believe it or not, from the phone company. There was an equipment charge every month. If you had a ham radio transmitter that would interfere with one of those, the phone company would actually come out and put an RF filter on your phone for free so that your phone would continue working. So if you have interference to a wired telephone, you'd put an RF filter on the phone. A part 15 device. Okay, this is a part 15. Whoops. This is a part 15 device. This is a part 15 device. Does anybody get where we're going with this part 15 thing? All right, so we are everything is part 15. We are actually covered under the FCC rules part 97. That covers amateur radio. That's actually something that I guarantee will be on your exam. Remember that number, part 97 of the FCC rules. Anything that is an unintentional or accidental or very, very low power radiator of energy is known as a part 15 device. That includes computer power supplies, that includes wall warts, that includes all that stuff. And in fact, if you look at the regulations, you will see that this is actually listed as a part 15 device. So is this computer power supply. And in fact, it probably even says so in the very, very, very fine print, FCC part 15. That basically means that as a part 15 device, it has to not interfere with other licensed services, including us. And it also has to accept all interference from licensed services. So it may be, let's say when you transmit, your computer power supply turns off. That's not really your fault. It may not be a good thing, but that's actually part of the design criteria of part 15 devices. It doesn't mean you can't improve it, but it means that it has to be built that way. Now, one of the implications of this is that, let's say your neighbor says, when you transmit, you're knocking out my computer power supply. You can say, I'm a licensed service, that's not my fault. Now, you probably want to help your neighbor out, but at the same time, you're not obligated to, because I'm a licensed service and that's a part 15 device and it's not my fault. Okay, so a part 15 device is an unlicensed device that can emit low power radio signals sent by a licensed device. on frequencies used by a licensed device. What should you do if something in your neighbor's home is causing harmful interference to your station? For instance, let's say they have a plasma TV. Well, you work with your neighbor to identify the offending device, inform your neighbor about the rules that prohibit the use of such devices that cause interference to your licensed service. Notice I keep saying licensed service. If you've got a license, you have special rules, right? That you have to follow, but also that you have special protections because you're licensed. And then check your station and make sure it meets the standards of good amateur practice. In other words, you haven't done anything wrong in your design. So about 5 years ago, I had a horrible nightly signal that was on 3.524 megahertz. If everybody pulls up your frequency spectrum chart, you will see that 3.524 megahertz is on the Morse code portion of the 80 meter band, which is one of my favorite bands to operate during the winter. And what I noticed was it was a carrier that just was a straight carrier, but sometimes there would be a voice on it. And I listened through it and I tuned around and I found that it was on FM, which did not make any sense, on 3.524 megahertz. After 2 months of driving and walking around my neighborhood, I gave up. After another 6 months, I said, I can't do this anymore. I grabbed the radio again and started driving and walking around the neighborhood, and I actually identified the house that it was coming from. And it turned out that I was helped out when I was listening to the fact that I actually knew who it was, and it was a telephone range extender that was using the house wiring in their house to create a phone jack in a room that didn't have a phone jack, using the electrical wiring in the house. And it was operating on 3.524 megahertz FM, but it was a very, very low power transmitter. But what was it doing? It was basically carrying signals from point to point so they could put their telephone calls in a room that didn't have a phone. Well, what's the problem with that? Every piece of wire can act as a what?
Antenna?
Antenna. So what they were doing was that they were transmitting their telephone calls all over the neighborhood, which meant that anybody could listen to their phone calls, for one thing, in addition to causing me interference. So as soon as we identified this and I told them what it was, she said, oh my God, I know what that is. Here, you can have it. So she pulled it out of the room and she unplugged it, pulled it out of the room and gave it to me. And I gave it to one of our local guys who works a lot with radio frequency interference and sources of interference. He was very happy to have it as an example of what not to do. If your signal is distorted or unintelligible, it could be that your transmitter is slightly off frequency, as we listened to. Your batteries could also be running low, in which case your FM transceiver might not be able to generate the signal that it needs to. You can also be in a bad spot. Now, a bad spot could be that you have reflections that are causing interference, multi-path interference. You could also be down in a valley and your signal's just weak. So if you can, you could maybe turn up the power, you could improve your antenna, you could go climb up on a hill, or simply move a couple of feet to one side. RF feedback in a transmitter or transceiver. Basically, if your audio sounds kind of like this, that could be the sound of RF being fed back in through the microphone. So basically, the output from your station gets back into the microphone, gets decoded, and it kind of messes with your transmitted audio. What can you do if your FM handheld or mobile transceiver is over deviating? This is an example of over deviating. Am I like way too loud now, everybody? Okay, so what's the solution? Because this radio typically is not going to have a microphone gain. If I want to get quieter, I would pull the microphone away from my mouth. Similarly, if I was using my handheld radio and somebody says, hey, you're just over deviating and your signal's distorting, that means it's taking up too much space on the band and the receiver can't pick it all up. So parts of your voice are being lost. You just basically back off. Okay, basic repair and testing. Okay, soldering, basic test instruments, and so on and so forth. Okay, which of the following measurements are commonly made using a multimeter? So there are three things that a multimeter will typically measure. It will measure ohms, volts, and amps. The most common, however, are volts and ohms, or voltage and resistance. So I'm going to pull up a picture of my classic Fluke 87, which I have for work. I love this meter. And here we go. This is my classic Fluke multimeter. So notice on this display, you can get it for 10% off. Notice on this display, we have on the dial volts with a little squiggly line over it. That would be AC volts. Then we have volts with a flat line over it. That's DC. And then we have MV for millivolts. Above that, we also have ohms. And then we have over on the right-hand side, we have milliamps, amps, and microamps. So those are three different settings for current. So this is, as you see, a $470 meter. And the reason that I bring that up is because I'm going to go to Harbor Freight. And here is my Harbor Freight 7-function digital multimeter. Okay, everybody see that multimeter? Well, look, it's got DC volts, it's got amps, it's got ohms, and it costs $7, and sometimes they'll actually give it away for free. Okay, so they both measure ohms and amps and volts. What are the differences between the $7 meter and the $400 meter?
The more expensive one's true RMS.
It's true RMS, that's right. Other things?
High voltage protection.
Yeah, that's the other thing. Well, you'll notice that this one right here says AC volts. There's a setting for 750 volts and a DC volts for 1,000 volts. The Fluke, which is the one that I have for work, also will work at, notice right there at the bottom, it says category 3, 1,000 volts, category 4, 600 volts. Well, okay, they have basically the same rating. Which one would you trust with your life if measuring 1,000 volts?
More expensive?
Yeah. The other one says it can use it. I would not go near it. The highest voltage I would measure with that is 120 volts. And I'd, from my wall voltage, and I might actually consider wearing gloves at the time that I was doing that too. My expensive meter, I will still wear gloves and a mask and stuff like that, but I will happily measure 480 or 600 volts with that because it's really, really designed for it. Okay, so what instrument would you use to measure electric potential or electromotive force? That would be called a voltmeter. How do you connect a voltmeter with a circuit? You want to measure the voltage of something. Essentially, you have a V. Here's your battery. This is a 12-volt battery, for instance. It has a plus and a minus. And what this does is it has a very high resistance and it allows a tiny current to flow. And it measures the current through its resistance. And it says, okay, E equals I times R. And it displays what the voltage is. You put this in parallel with your circuit. Notice these are two parallel lines. Thus, your voltmeter is in parallel with your circuit that you want to measure. When measuring high voltages, don't use the Harbor Freight multimeter. Make sure that the leads that you're using are suitable for the voltages that you're testing. And we're on page 65, by the way. Okay, for measuring resistance. Here we go. Now we're going to measure resistance now. So we have a resistor. And here's our ohm meter. Okay, now, do you see any power source in this circuit? There's no power source in this circuit. Well, in order to test something, what are we going to have to do?
Power it up.
Power it up. Well, the way we power it up is that there's actually a battery in this meter. And the way that this works is inside this ohm meter, there is a battery and there is a current meter. So what do? We put a small voltage through this and we measure what the current is. And guess what we use? Ohm's law, E equals I times R. We don't know the R. R equals E divided by I. It calculates that for us and it tells us what our resistance is. So what do you think would be the problem if we were doing this and our meter was right here as it was, and this was still connected to a battery? What did we already say was inside that meter?
Battery.
A battery. So what will happen? Where is the preferred path of current for this meter, for our own meter? It might just go right through the battery. If this was a 24-volt battery, what have we suddenly done? Which is the bigger battery? We're now stuffing current in a reverse direction through our meter. And there's a fair chance that we're going to destroy our own meter. And that is why you have to make sure when measuring circuit resistance that the circuit is not powered. And in fact, what you may need to do is actually, in order to not power it, you may actually need to do that and disconnect the battery. You might actually have to, if you want to test a resistor, unsolder something in order to do it right in the circuit, to make sure before you replace it that it's still okay. Things that can damage a multimeter: attempting to measure voltage when using the resistance setting for that exact same reason. What is probably happening when an ohm meter connected across an unpowered circuit indicates a low resistance and then shows increasing resistance with time. So what we're going to do is draw our multimeter. We're going to use it in ohms setting. And remember, what did I say was inside a multimeter for ohms?
Battery.
We have a battery and a small ammeter. Okay, so, and it calculates R equals E divided by I. Well, we're getting our I directly from here. So let's say that it sees a short circuit. What would the resistance be?
0.
0 ohms. That would be a 0 ohm load. Okay. What would an open circuit be? How many ohms is an open circuit?
Infinity.
Infinity ohms. That's right. Okay. So now let us say that we measure across an unknown circuit. And we get over time a resistance that goes like this. And it starts at 0 and goes to infinity. Has anyone ever seen this?
Yep.
Okay, so the mystery device in here is a capacitor. Because what happens when a capacitor is not charged at all? Are you able to dump current into it and charge it up? The answer is yes. And it takes a lot of current, right? Well, by Ohm's law, what happens is it says, oh, we have no resistance. But then the capacitor eventually gets charged up, and how much more charge could you stuff into it? How much more charge can you stuff into a capacitor that's fully charged?
None.
Which means you have no current. And if you have no current, it's an open circuit. So if you test a circuit and you get a curve that looks like that, and it starts at 0 resistance and goes up to infinity, what you'll end up with is knowing that there's a big capacitor in there that you just charged up. And that inside that circuit is a capacitor. Okay.
Could you use the ohm meter to calculate the resistance of a circuit, say with all the various components in it? So if you had
Sure.
a wire and fittings and fuse and all
Sure.
that, you could calculate the voltage drop?
Absolutely.
So
Yeah,
you
because
add,
can,
add up all the resistance of all the different pieces, or if you didn't have it put together, and you could add up with all the various pieces and figure out if those were going to work for the current and voltage you plan to put through.
so let's say that you, let's say here's your circuit and you have, whoops, let me make it red and black. So here's your power. And you know that this is 22 feet long. And this is 22 feet long. And you have your transmitter. And that's going to pull 10 amps. And here's your power supply. And you set this for 13.8 volts, which is your nominal battery voltage. It's not actually 12, it's 13.8, but it's close to 12. And that's actually 6 times 2.3. 2.3 volts is the voltage of a fully charged lead acid battery cell. That's the cell voltage. And that's how we get 13.8. As it starts to come down, it goes down to 2 volts, and then we get 12 volts. Fully charged, it's 2.3. Okay, so as we do this, what we can do is we have this path, and we have this path, return path. So we have 44 feet of cable of something AWG, which is wire gauge, and we have certain amount of ohms per foot, and it's linear. So you can basically use that to figure out what your total resistance is. And knowing that this is your current, you can figure out what your voltage drop is. Similarly, I can also do this. Use this for work all the time. Calculate your voltage drop. Notice it's by south wire because they want to sell you the right size wire too. So notice there are lots of these out here. Voltage drop calculators. Here we go. So we go with copper. We go with, let's say, 10 gauge material of conduit. We have no conduit. Don't deal with the power factor. And it's 12 volts, DC, single set of conductors. And distance one way is, let's say, 50 feet. And we're pulling 10 amps and go. There we go. So given those parameters, voltage at the end, we have 10.8 volts. So if I were to increase this to, let's say, 13.8 volts, it should increase it to about 12 volts. So there's 12.6. If I were to increase this wire gauge to a number 8, I should see my voltage increase. If I increase this to number 6, which is even bigger, now I'm even better. The other thing I can do is I can shorten this up to, let's say, 25 feet. Now I have even less loss. So this is an incredibly useful thing to have handy. That way you don't actually have to go and look up what the individual wire resistances are. It's already
What about all the components in between, like maybe a fuse or a switch and things like that? Is it rather insignificant?
It's for the most part, it's insignificant. A fuse is going to add, a tenth of an ohm. You can certainly figure it in. Connectors like Anderson power pole connectors, they do not have zero resistance. So yeah, you can work all that into. And the other thing is that you can actually build it all and then test it out also. You can see what your overall resistance is, and then predict what the numbers are going to look like. Okay, soldering. The best type of solder for radio and electronic use is known as rosin core. And the reason that we use rosin core is because rosin is the same stuff that you put on let's say a violin bow. And for that, it tends to smooth out the playing as the bow slides across the strings. In the case of solder, we burn it. And essentially, as it burns, it cleans off oxidation and sends it off into the air as smoke. Because of that, it's not recommended that you breathe too much of it, which is why if you're going to be doing a lot of soldering, you probably want to use a ventilated space or a fume hood that will suck out the solder smoke. A cold solder joint will have a grainy or dull surface. A good solder job is something that's bright and shiny and looks like a little volcano, or a perfect mountain without a crater. When you see a crater in the center of it, that's actually setting you up for trouble, because that can be a cold solder joint. The trouble with a cold solder joint is that it basically means that your material was not hot enough to flow to the things that you were soldering together. And it may be mechanically held in place, but sometime in the future, typically when you're out in the field and have no access to a soldering gun, it's going to work its way loose, and then your thing will stop working because of Murphy's Law. All right, FM operating procedures, page 67. Yes, do we have any questions before we go? Okay, page 67. Once you get your license, most people, the first thing they do is buy a VHF, UHF, FM transceiver, which allows you to get into repeaters and do public service and things like that. An amateur station that simultaneously retransmits a signal of another station is known as a repeater station. So the tricky thing with a repeater, of course, I'm going to bring this up right now, because why the heck not? So let's say that I have one antenna here and one antenna here. And this is hooked up to my repeater receiver. And this is hooked up to my repeater transmitter. In between, I have a controller, which is basically a computer that determines whether or not the received audio is allowed to be sent over to the transmitter. Each of these is connected to an antenna. And my receiver is operating on 146.72, and this is transmitting on 146.12. Okay, what do you notice about those two frequencies? Anybody?
They're offset by
They're
minus
offset.
0.6.
Right, offset by negative 600 kilohertz. That would be a negative offset. Okay, but what else do you notice about them? They're on the same band, and they're actually fairly close together. I'd probably get away with it like this, but a lot of repeaters are not built like this, believe it or not. A lot of repeaters, because you have essentially a box where your equipment is, and it runs up to a tower, it's really expensive to have two antennas. So what you actually have is a single antenna that works on the receiver and the transmitter. But what we said is that everything that comes into the receiver is transmitted on the transmitted by the transmitter at the same time. Does anybody see a problem with this? If they're using the same antenna, is there not a connection between the receiver and the transmitter at the same time?
They'll interfere with each other?
What will stop the transmitted signal from also going back into the receiver?
Directional
Thing.
coupler.
Yeah, well, right. And that is, you have to have a filter. You have to somehow separate this frequency from this frequency. They are in the same band. That is not an easy thing. So what we're going to do is show you how that is done. We're going to put a box here And this is called a duplexer. And what do you think a duplexer is? It starts with the letter F.
It splits the frequency or the time of transmission.
No, it does not. It can't, because you're always transmitting at the same time.
Oh, it doesn't send a little bit of transmit and send a little and
Nope.
wait for a little.
Can't do that because it's always on all the time. What is a duplexer?
It's a filter.
It's a filter, and it's not just any filter. It's a special filter because if we're transmitting, let's say 100 watts of transmitter power, and this is such that our receiver is basically saying if it gets anything greater than 0.000000001 watts back in, it's not going to work. That's like 110 decibels between the transmitter and the receiver. There has to be like 110 decibels of isolation. What does that look like? That looks like this. Anybody ever seen one of these? That is a duplexer designed to operate on the 2-meter band and VHF. Notice how much it costs. That is just a simple filter. Okay, so each one of these is a metal can with a plunger. And notice in the top, there's this little screw. Essentially, what the screw does is that it inserts the plunger to a given depth. And what this thing consists of is low pass filters and high pass filters and band pass filters. And each of them has enough isolation that it allows you to use the same exact antenna connected through all these cables so that you can use the receiver and the transmitter and they won't interfere with each other using the same antenna. But again, notice how much it costs. Not to mention the fact that, they're about 3 feet tall. This is not something that just like, fits in the palm of your hand. This is like 3 feet tall and 1 by 2 feet, 1 by 3 feet, this pack. So that is why, notice it can handle 350 watts, 400 kilohertz frequency separation, 2 dB insertion loss. So there's a little bit of loss, but not bad. 100 decibels of isolation between the two sides. So the other thing is that once you get it, you actually have to tune it. You have to have somebody with the ability to tune it, which is why most people don't just go willy-nilly and put up their own repeater. That's why most repeaters are put up by clubs, because in order to make one work, it costs some money. You have to have some serious hardware, not to mention space. Okay, so that is a fundamental part of a repeater. What types of amateur stations can automatically retransmit the signals of other amateur stations? A repeater station, which we've already talked about. There's also an auxiliary station. An auxiliary station is basically like a link on a mountaintop that nobody particularly listens to, but it's used to connect two stations together. So it sort of acts as a repeater, but no one's listening to it, not directly. And a space station. A space station can actually have a repeater on board, like the International Space Station. Satellites, anything over 50 kilometers up is considered a space station. So they're allowed to be repeaters in space. Which of the following describes a linked repeater network? We have one here in Oregon that links 50 different repeaters together. That would be a network of repeaters where signals received by one are repeated by all the repeaters. Those are typically linked together by microwave links or by UHF links, or those would be considered auxiliary stations that link them together. The nice thing about that is that it creates a very wide area net where people in one place can talk to people in another place just by using their handheld radio. And that Oregon, for those of you who don't know, is a pretty big and mountainous state with a lot of varying terrain, going from desert to ocean to snow-capped mountains and so on and so forth. So, okay, to use repeaters, you have something called an offset. Once again, what is the standard offset on the 2-meter band in kilohertz?
600.
600 kilohertz. So it can be either plus or minus. So what we're going to do is look at the Oregon Repeater Relay Council. Every state has one of these. Here we go.
Do we have a handy list of offsets and bandwidths for different bands?
The only ones that you really need to know are 2 meters and 70 centimeters. But
why do we need to know 70 centimeters?
Are you going to use it?
I have no idea.
Exactly.
So then why do I need to know it?
Because you can use it. Because you could use it. And that is the second most active band for technicians. So for 2 meters, it's 600 kilohertz. For 70 centimeters, it's plus or minus 5 megahertz. What's nice about that 5 megahertz spacing is that it's a lot easier to build a duplexer for that because they're further apart. And on top of that, they're only 1/3 the size because everything is only 1/3 the size because the frequency is 3 times higher. So if you were to look at, let's say we go up to the 440 megahertz, notice that you have, for instance, in Kino, 440.6750. By convention, here's your offset. It's 445.6750. So it's a 5 megahertz offset. And you will see that in some cases, the ones that are higher in the band, like 440, no, I guess there aren't any that go negative in this case, at least not in Oregon. The other thing is that on other bands, the offsets are not really set in stone. So like for this 224.02, 222.42. So that's 400 kilohertz, but those are not set in stone. You look at another frequency band, which would be 6 meters. And like, for instance, this one is, let's see, 1.7 megahertz. And there's another one here that is not 1.7. I can't remember which one it is, but they're not all the same, just to be confusing. Here, there we go. This one is this one's what? No, it is also 1.7. Well, you'll find some odd offsets on the bands that aren't 2 meters and 70 centimeters, depending on where you are. And the reason that this company, well, I won't call it a company, but basically this council exists is because we don't want the FCC telling us, you know, do this, do this, do this, do this. We want them basically saying, hey, here are the frequencies you're allowed to use. Now go and figure out how to use them and stay. And you're not giving us any money. So go figure it out on your own and don't cause any trouble. So we basically have this organization in Oregon called the ORRC, and every region has one. And this is a group that is essentially set up by repeater owners to keep the peace and assign frequencies within the bands. Again, we don't want the FCC telling us what to do. We can handle it. So we choose to do it. So here's the 2 meter band plan. So with a very few exceptions, this is not part of the law. The only thing that's part of the law is, notice here where it says at the very top, CW. By law, those frequencies, so 144.01 to 144.10, are Morse code only. That is the only thing that's codified in law on this band. I can look at the 6 meter band and find that, notice from 50.0 to 50.58. No, it's not even listed there. Here's another one. And here's another one. So anyway, there are just a few bands that they've actually specifically said thou shalt not do anything but this. And we like it that way, because we can take care of it ourselves.
Now, can anybody use a repeater, or do you have to join a club?
Anyone, most repeaters are open, in which case you know, we want people to talk to us. So we put up a repeater as a resource, and we make it available to anybody who has a license to go ahead and use it. There are some repeaters that are closed, but they're very, very rare. Okay, what describes the use of a sub-audible tone transmitted along with normal voice to open the squelch of a receiver? That would be CTCSS, also known as PL or private line. We're on the top of 68, by the way. If you're unable to access a repeater, even though you can hear the repeater really loudly, number one, you might have the transmitter offset set wrong. You're not transmitting on the right frequency for the receiver to hear you. You might also need to set your CTCSS correctly. It might not be turned on. It might be that it's listening for a frequency of 156.7 hertz, and you have it set for 100.0, in which case it won't be heard. You could also have to set the DCS tone properly. Again, that's digital code squelch. It operates very similar to a CTCSS. A station that's not strong enough to keep a receiver.
So
yeah.
the CTCSS is there to maintain communications open at all time, because it in essence activates the squelch.
No, it actually deactivates the squelch.
Well, that's what I mean. Yeah. I mean, in essence, it keeps it open so you're always hearing something.
It keeps it open so you're hearing only the station that's using it properly.
And so when you do you need to do something to have CTCSS active?
Yeah, it's typically a setting that you'll program into your frequency, into your channel.
And you do this because
the receiver on the repeater is built that way. And again, the reason that systems are set up like that is because of the way
noise, right?
Because of the way FM works. So let's say that we're looking at the LA basin, which is ringed by mountains, right? And you've got so many repeaters set up around the LA basin that you end up with, because there's only a limited number of different frequencies you can use. So here's 1, 2, 3, 4, and 5. If I am this person sitting down on a park bench in the LA basin, right? It's ringed by mountains, and I just transmit on a frequency that each of these repeaters is listening for, which of them will activate if there's no CTCSS set up? All of them, which means I'll hear this and this and this and this and this, and so will everybody else. And because these are operating on FM has that nasty habit of this thing called the capture effect again. And the capture effect says that the strongest signal wins, or they all obliterate each other. So who gets heard?
Strongest signal?
Or nobody.
Or nobody. That's right. So what if I want to use repeater number 2 only? These are all operating on the exact same frequency. So I have to have some way of differentiating so that I'm only using number 2. So if these are set up for 88.5 and 67.0 hertz and 100.0 and 123.0 and 156.7 hertz, I know that if I only want to activate repeater number 2, because maybe I actually want to talk to somebody who's over here outside of the basin, who can actually get into repeater number 2. I will cause my transmitter to transmit a signal with that subtone of 67.0 hertz, so that the only repeater that's activated is number 2. Therefore, when it transmits, the only signal that will be transmitted anywhere in this valley, so long as there aren't multiple people using that frequency, is number 2, and I will actually be able to hear it. And that's why we use. Does that make sense?
Yeah.
Okay. Okay, let's see. If your station's not strong enough to keep a repeater squelch open, which of the following might allow you to receive the station signal? And that would be to use the reverse function on your radio and listen for the transmitter on the input frequency. So let's say that here's a repeater way over here, and here's station A, and here's station B. And station A is supposed to be transmitting to the repeater, and you've got a much better antenna than station A does. You can actually get into the repeater just fine, but station A is down in a valley and can't. Well, you might actually be close enough that you can hear station A directly. So if station A does not have a good path to the repeater, then it's entirely possible that you might actually just be able to hear them transmitting directly. So if you listen on the same frequency that the repeater is listening for, you might actually hear them, in which case you could then contact them and say, hey, let's go to simplex and just work directly, and thereby avoiding using the repeater altogether. And this would be known as, you'd set up your radio for reverse split, which means you're basically listening on the input and not the output of the repeater. You're essentially now duplicating what the repeater's doing. You're basically listening just like the repeater is. Okay. Another problem you may encounter is over deviation, which can occur if you're speaking too loudly. If somebody says your transmissions are breaking up on voice peaks, here is the main reason for that. We're going to look at a repeater's receiver is listening for, let's say, plus 5 kilohertz from the center frequency and minus 5 kilohertz. So listening in this window, your signal when you talk will spread on because it's frequency modulation. You're going to spread out. There's a modulation index in your transmitter, and let's say that it's too hot. Your deviation is too hot, and it comes out to -7 and +7. Well, what's the repeater listening to? It's listening to -5 to +5. So all of this stuff that you're sending right here will not be received. That contains information about your voice, which basically means that because some of your signal is not actually getting there. So if you're over deviating, that means you're talking too loudly, which means talk quieter or back away from the microphone. How do you call another station on a repeater if you know the other station's call sign? Alpha Alpha 8 Japan. This is November 7 Juliet India. You there, Pat?
Yeah, I am.
Oh,
This is Alpha Alpha 8. This is Alpha Alpha 8 Juliet.
All right. So I just called Pat. You say the other station's call sign, then say your own call sign. Yeah. What indicates that you're listening on a repeater and looking for a contact? Easiest way to do it. This is N7JI listening. Just state your call sign. It makes the transmission legal and indicates that you're there if somebody wants to talk with you. If you're transmitting and receiving on the same frequency, that's known as simplex.
Wait a minute. So then somebody's listening and then they go, okay, whatever it was.
Here, I'll do it. Here,
N77 blah,
we'll
blah,
do it.
blah.
Here, we'll do it. This is N7JI listening. Go ahead, Pat.
This is Alpha Alpha 8 Juliet. How are you doing, N7JI?
Hi, Pat. AA8J, N7JI. Teaching a class. How's it going today? Over.
Class is going really well. AA8J for ID. What is our estimated time of completion today?
This is N7JI. Well, Pat, I'm hoping we're done by noon. We might go a little bit over, maybe 11, maybe 12:15. And that should give everybody a chance to go get lunch and do a little studying and get ready for their tests. Over.
This is A8J. N7JI, that's awesome. And I'm looking forward to seeing many people take their exam today. I need to clear out of here. So this is Alpha 8 Juliet, clear.
All right, take care, Pat. AAHJ, this is N7JI, clear. So we just had a contact over a repeater. That's exactly what it would sound like.
So sometimes you copied your call sign and sometimes you didn't.
Yep, you have to ID your station every 10 minutes and at the end of the whole thing.
Yep.
So you didn't have to identify yourself as many times as you did.
No,
No.
we just got into that where we did.
Some people do it more than others, and it helps you remember the other station's call sign if you do repeat it a couple of times. That's been my biggest struggle as a new ham.
Yeah, my biggest struggle is the fact that I get a lot of people who I teach who end up getting licensed and get on locally, and we get a lot of new call signs here. So, you know, I can remember a few call signs, and once I've talked to somebody 5 or 6 times, I remember their name and call sign. But when you start getting a flood of new call signs to remember, it's really hard. So.
But if you're trying, so you just said, hey, here I am and I'm listening.
Yep.
Anybody can pick you up, right?
Yep.
But what you did is you picked a specific repeater. So if let's say there's a repeater in Pocomo and you wanted to talk to, hey, what's the weather in Pocomo? You would pick that repeater and you would use your call sign and say you're listening.
Yep.
And that's it. And if somebody goes, they pick you up, then you start the conversation.
Exactly. And sometimes, like I was in Lufkin, Texas on work, and I knew that there was a repeater nearby, and I didn't know what kind of activity was on it, but I knew there was a pretty tall one, and I just went on and said, N7JI portable 5, anybody around for a quick contact? And somebody answered, one of the usual users of the repeater answered, and we had about a 15-minute conversation. And then there was a net, and I checked into the net and talked to a bunch of the people there. So yeah, that's kind of how it works. Okay, so what is the point of using
Nate wants to tell you something.
Oh, Nate, I'm not used to looking for hands up. What's up?
My dad's a ham, so he lets me use it sometimes.
Yep.
And I always use monitor, and I do the call sign at the beginning.
Mm-hmm.
I go KJ7 USI monitor.
Yep. Everybody's got their own way of doing it, but the only thing you have to do to make it legal is just give your own call sign.
Don't you have to do it at the beginning?
Nope. We're getting there. Okay. Why are simplex channels designated in VHF, UHF band plans? So if we look at that band plan again, you will see that we're going to look at the 2-meter band plan. And notice there are about 2/3 of the way down. 146.42 to 146.60 in Oregon. It says simplex. 20 kilohertz channels. And the reason that exists is, and there's another one from 14740 to 14758. The reason that those are there is that they make sure that there are still coordinated, known, available frequencies to use for simplex FM. The national calling frequency for FM simplex in the United States and Canada is 146.52 megahertz. So while I go down to the next section, a funny story, I was in Humboldt, Saskatchewan. Anyone ever been to Humboldt, Saskatchewan? Pat, have you ever been to Humboldt, Saskatchewan?
No, that's a goal of mine, something on my bucket list.
Yeah, okay. Humboldt, Saskatchewan is just, it's about 50 miles east of Saskatoon. And I'm there on a winter night and I just can't drive any further. So I pull into Humboldt and get a hotel. And I'm like, okay, well, I'm going to call out on 5.2 and see who's around. Ha 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 ha. And so I did. And nobody answers. And I hop in the shower and I hop out of the shower and I hear, the station calling. What was that call sign again? I'm like, oh, that was weird. And I go over to the radio and says, N7JI portable VE6 over. And it turns out that the guy said that his wife had heard somebody calling on the simplex frequency. But that was a few minutes ago. And anyway, we ended up having a 45-minute chat just in Humboldt, Saskatchewan, population 7,000.
Yep.
So, and that was again, because it was on the simplex calling frequency. All right, HF operation. We're on now page 70. On the HF band, signals can be easy to copy or difficult to copy. So this is something that you do not do on a repeater. You only do it if it's not a repeater. You call CQ, CQ, CQ. CQ means literally, I'm seeking somebody to talk to. CQ means calling any station. Again, you don't do that on a repeater because there's a repeater station there, and the assumption is that you're going to be picked up by the repeater. For instance, though, if you're on simplex, you could call CQ because there's no repeater there to listen for you. When calling CQ, make sure you're in your assigned band. In other words, you have to look at that frequency chart and make sure that you're actually legal to be there and transmitting. If you're not legal to transmit there, don't transmit there. Then you listen to make sure if the frequency is being used, and then you actually ask if the frequency is in use. And the reason you might do that is because we have, when you get into things like propagation, you will start to notice strange things. Like if you have station A and station B and station C, station A can hear station B, and station A can also hear station C. But these stations, B and C, cannot hear each other. So they don't know that the other one is there. So let's say that you have a conversation that's ongoing between A and B, and you are station C. And B is jabbering away, has been going on for 5 minutes, right? You say, oh, well, I don't hear anybody on this frequency. Okay, I know I'm allowed to be there. And then I ask, is this frequency in use? Station A hears you and says, yep, frequency is in use. Because if you had just started transmitting, you, unbeknownst to you, would have actually been interfering with station B because there is no path between B and C. So when might this kind of thing exist? We actually looked at this yesterday when we saw that, what did we have? We had the West Coast, and on this particular band, we had a string of stations that we could hear. And then we had, at a longer distance, another string of stations that we could hear. And all of these stations in between, we had no copy on. But if there was another station, like let's say right here, they would actually receive, about the same stations. We might actually be far enough away, but still so close that we actually couldn't hear each other. This is actually very common in working across, for instance, the United States, where let's say this is Eugene and this is Seattle, where we don't even know that the other one's there. We can't hear each other at all, but everybody can hear the station from all the way across the country. Okay, how do you respond to a CQ? All right, Pat, you're on the spot. CQ.
Wait.
Yes.
So right before that, it says you don't want to start calling CQ willy-nilly.
Correct.
Meaning what?
Well, in other words, you have to listen.
I know.
It means you have to listen and make sure. This is exactly why you don't want to just start calling CQ. Because you want to make sure that that frequency, to the best of your knowledge, is actually available.
Okay, so it's not the use of
Oh,
CQ
no,
should
no,
be
not at
used.
all.
Okay, all right.
All right. Pat, you're on the spot.
CQ, CQ, CQ. This is Alpha Alpha 8 Juliet, looking for contacts in Oregon.
Alpha Alpha 8 Juliet. This is N7JI, November 7 Juliet, India. Over.
Well, greetings, November 7 Juliet, India. How are you doing today?
AA8J. This is N7JI. Good afternoon. My name is Scott, Sierra Charlie Oscar Tango Tango, located in Eugene, Oregon. So I fit your criteria. Over.
Great to make your acquaintance. N7JI. Actually, I should be using alpha modes, right?
Nah, you don't have to use phonetics because
Okay.
we already did that.
And can you give me a radio check on how I'm coming in your location?
Yeah, Roger from N7JI, and I need your name as well. You're actually coming in about a 5 and 6, 5 and
Okay.
6 with a little bit of QSB. So again, my name is Scott, Sierra Charlie Oscar Tango Tango. Over.
Yes, this is Alpha Alpha 8 Juliet. The first name is Pat, Papa Alpha Tango. And thank you for the radio check on how I'm coming in. And what county are you in?
Okay, Pat. Thanks for that, Pat. I'm in Lane, Lima Alpha November Echo, Lane County. Over.
Okay. Are we done?
Well, you didn't sign yet.
Oh, okay.
You got to do salutations.
Okay, I'm gonna call 73, got a phone call. So thank you for the contact, November 7, Juliet, India. This is Alpha Alpha 8, Juliet, clear on your last.
Okay, AA8J, this is N7JI. Thank you, Pat. And nice to meet you, and have a good afternoon. And glad to give you a decent signal report. I hope everything's well there. AA8J, this is N7JI, clear. Okay, so.
Boy, that's a really inefficient way to talk.
It is.
Holy Toledo.
Some people get more relaxed and don't use their call sign every single time, but if you're in a QSO or a contest, things go really fast.
I'm not sure I'll ever want to be in a contest.
Oh, well, it depends. Are you a competitive person?
Yeah, but I pick my competition.
That's right. Well, there's, for me, contesting is a lot of fun. That's why I do it. And it's also a good way to work a lot of to talk to a lot of different countries, a lot of different people.
What's a contest?
Contest is literally an event where you try to make as many contacts in as short a period of time as possible over and based on some criteria. So like, for instance, yesterday was the Arizona QSO party. The goal was to make as many contacts in the state of Arizona in as many counties as you could over a 12-hour period. And I finally got on at it ended at 10 o'clock local time. I got on at 9:15.
Gee, how many contacts?
13, 14.
That's not bad.
Wasn't bad. Something like 10 or 11 different counties. I snuck Coconino County in there as in the very last minute.
That's cool.
So let's see. It's important to always identify your station, even when only performing tests. Which of the following is required when making on-the-air test transmissions? That would be just to identify the transmitting station. Always have to identify your station, even if it's just a test. This is something that's going to come up over and over as we talk. Which Q signal indicates that you're receiving interference from other stations? That would be QRM. The reason that we use Q signals is because Morse code was the way that hams learned to talk. And it's a lot quicker to say QRM than I am getting interference from somebody. So these are amateur radio Q signals. I happen to do a lot of Morse code, and they greatly simplify things. It's kind of like a canned message. The other thing that you'll say is QSY. QSY means shall we go to a different frequency, or let's change the frequency. So those are two of them those are the only two that could show up on your technician exam. QRM, which is, again, man-made noise, is my transmission being interfered with. And the other one is QSY, which means you're getting, you're desiring to change frequency. A band plan, again, what is a band plan? This is a band plan, something that ORRC has put out, for instance, like we saw. It goes beyond what the FCC has said. We like it that way because the FCC basically says, stay in this region. Here, these are the frequencies that you're allowed to go into. And beyond that, the band plan basically sets up a gentleman's agreement that says, this is, these are the rules that we have set up to keep the peace, to make sure that we don't have a lot of interference situations occurring. So it's a voluntary guideline for using different modes or activities in a band, in an amateur band. Another basic tenet of amateur radio is to operate courteously. So who owns a frequency? If two stations are operating on the same frequency, who is in possession of it?
Nobody?
That is nobody. That's right. No one has ownership of a frequency, even if they've been there. Let's say on 7.285 megahertz, which is in the 40-meter band, I have run a net that has been active for the last 40 years every day at 8 o'clock local time on that exact same frequency. Somebody's already using it. Well, there's something that basically says that the net frequency is probably going to be 7.8285 plus or minus QRM, which means QRM, again, is interference or noise or other people. So if there's somebody already there, you might say, okay, well, the net's going to be up or down in frequency a little bit. You could also ask, hey, we're running a net here in 5 minutes. Could you guys move a little bit? And the answer would be, yeah, okay, we'll go down 5 kilohertz. Because again, nobody has ownership of a frequency. Okay, so now we're on page 72, public service, emergency communications. Amateur radio emergency service is ARES, ARES. ARES is very similar to RACES, which is the Radio Amateur Civil Emergency Service. The only difference being that RACES has the word civil, which is government related. So ARES is an organization that is run by the American Radio Relay League. And you basically sign up and register yourself and your equipment for communications in the public service. RACES is a sort of parallel organization, but it's actually organized by government agencies for civil defense and emergency management. So it involves people, frequencies, and communication and equipment. They both involve frequencies, people, and communications equipment. ARES does not have the word civil in it. RACES has the word civil, RACES, which basically means that it's run by governmental organization. And you register with that organization. They both can provide communications during emergencies.
Is
Pat,
CERT,
yeah.
excuse me, is CERT considered a government organization?
Typically it is because it's sponsored by FEMA.
Okay, so, okay, I participated in both then.
Yeah. So Pat, what's an NCS?
Net control station.
Net control station. Okay. NCS is net control station. So if you are running a net, that means your net control. A net is basically a short for the word network. It's an on-the-air communications method for people talking with each other. One basic thing is to remember is that unless there's an emergency, net control will be in control of the net. And you stay on frequency unless you have to leave, and you don't speak unless there's an emergency or you're asked to speak by net control. So if I were net control, I'd say this is N7JI net control for the in-class net. Do we have any check-ins? Please come now.
This is Alpha Alpha 8 Juliet.
All right, AA8J, thank you for checking in. I've got you on the roster. Do we have any other check-ins? Please come now.
This is XYZ Homer Turnbuckle.
XYZ Homer Turnbuckle. I like that name. All right, I've got you on the list. Please stay around and we'll get back to you. Any other check-ins?
This is KJ7 USI, Nate Swank.
Okay, KJ7USI, I've got you on the list. Okay, so we're going to ask and we're just going to go through the list and see if anyone's got anything to report. AA8J, Pat, you got anything? Over.
Yes, net control. This is AA8J, and we have beautiful 75-degree weather here. Finally clear of storms in the Bronson, Michigan area for at least for a couple of days, and looking forward to the nice sunshine this afternoon. Back to net control. Again, this is Alpha Alpha 8 Juliet.
All right, AA8J, thank you, Pat. Okay, Homer, have anything for the net? Over.
This is XYZ Homer Turnbuckle. Happy to report that we have 5 trees down. The ice storm came through. Haven't seen CPI. No, this is what happened this last winter.
Yeah.
This is exactly what happened where I live.
Oh, I'm sorry.
So, yeah. So anyways,
Keep
that's what I
going.
gotta, that's
Okay.
it. I'm out, or whatever you say.
Okay, you just say back to net.
Back to net.
Back to net. Thank you. Okay, thank you. Thank you for the report, Homer. Do you need any assistance there? Over.
No, not at this time. Checking with the neighbors to see if anybody's hurt. We'll be back. Out.
That's good.
Okay, so back to net. And the other thing to do is always identify yourself, then back to net. That keeps it legal because it might not come back to you and you have to identify at every 10 minutes and at the end. So you don't know when it's going to be the end or the next time you're going to get called.
Right.
So,
Okay.
okay. KJ7USI, over to you.
KJ7 USI, it's really hot here and I really need some ice. Can I please get some?
Okay, now you got to turn it back to me.
KJ7 USI out.
You say back to net. Just say back to net.
Back to net.
Okay, KJ7USI, I get your request for ice. Do we have anybody who can deliver any ice over to KJ7USI? Please come now.
This is Alpha Alpha 8 Juliet. I can definitely deliver some ice to KJ7 USI. Back to net control. This is Alpha Alpha 8 Juliet.
Okay, AAHJ, thank you very much. KJ7 USI, I have a report that AAHJ will be delivering ice over to you. Over.
Am I supposed to say something now?
Yeah, you have to acknowledge it.
KJ7 USI, I can use some ice. Back to net.
Okay, KJ7 USI. Okay, thank you, Pat. AAHJ, go ahead and make a delivery over to KJ7 USI. Over.
Roger, Roger. This is Alpha Alpha 8 Juliet, in and out for the time being.
Okay, thank you. This is N7JI. If we don't have any more check-ins, I'm going to shut down the net just so we can get back to class. N7JI, any last check-ins before we go? Okay, nothing heard. This is N7JI securing the net at 11:10 Pacific time. Thank you, everybody, for checking in. The frequency is returned to normal use, and you're all free to go. N7JI clear. So basically, that's how you would set up an ad hoc network. And that's why we practice, because the more times you do it, the better you are at it, the more comfortable you are.
So are these networks already in place, like Pat was talking about CERT and other places, so that now we all graduate with flying colors and we get our call signs and we buy our equipment and we now, say, okay, we're going to be part of the CERT network or whatever the races or whatever, so that we can help out in case of emergency?
It's always recommended that like basically practice makes perfect. So we do nets even when there's no reason to, so that when everybody is ready to, you are used to it. You know what frequencies to use, you know how to get, how to be net control, how to keep the traffic down, because only one frequency can be used by one person at a time. So Yeah, that's why, we tell people, it's great that you got your license. It's great that you got your radio. If you leave it in a drawer and you never use it, when the time comes, you're not going to know what to do. So it's like any skill. The only way to stay good at it is to keep doing it. So that's why.
I initiated just after getting my technician license and building a 2-meter antenna, quarter plane ground, quarter, whatever. Anyways, I just pinged into the local station that I could reach and practice from there. And it takes a brave soul to be NCS for the very first time.
It does.
That's all I can say. Because you're having to listen to a lot of different call signs that you're not familiar with.
Yep.
So, but my recommendation is to get involved immediately. However, check out your local stations and find out when their net meetings are, emergency net meetings, even their siren check meetings, which is in Michigan, it's the first Saturday of every month, and we're all mobile because we're checking the sirens.
In Oregon, we do the shakeout drills because we're in an earthquake zone.
You do the what?
Shakeout.
Really?
Yeah.
I'd love to participate in that.
Yeah, we do shakeout stuff.
That's cool.
Test out our nets and things like that. Because
yeah. Also in the Eugene area, there's a net for new hams.
There is. It's called the Now What Net on Monday nights.
Exactly. So just pointing that out for folks that are local.
Your mom is one of the 3 founders of that net.
I know. She's been practicing being net control, and she feels more comfortable with it now. And yeah, I hear about it a lot.
Yeah, no, I bet. And actually, one of the cool things about contesting is that it's often said that contesters are the best operators that you'll find. And the reason that contesters are the best operators is because during a contest, the conditions are usually really crappy. You get a lot of noise and you're trying to dig signals out of the noise so you can make contact with them.
Right.
No matter how bad the signal is. So you get used to repeating your call sign 25 times, screaming into the microphone, or listening really, really hard and becoming, and getting really comfortable. You spend a lot of time on the radio. And if you spend a lot of time on the radio, you get good at it. So,
yeah, you do.
All right. So continuing on page 73, what's an accepted practice to get the immediate attention of net control? And that would be saying emergency. In some nets, it's break. In some nets, it's priority.
Break.
So, and that's basically saying, I'm supposed to be sitting on the side, but I need your attention right now. N7JI with an emergency call. Fortunately, I've never had to do that, but that's how you would do it. So formal traffic that you would pass from one person to another is known as traffic. So when you're on a net, you pass formal messages called traffic. That is basically information that can be health and welfare. It can be just like Nate said, the traffic would be need ice, right? That would be the message. That's an official message that net control would handle. It's also possible if, let's say we're using a repeater and I know that both AA8J and KJ7USI are able to get into the repeater. I might say, okay, it's okay to go direct, go. In which case, I just want you guys to communicate, and both of you, when you're done, hand it back to me. So basically, net control runs the show. It's kind of a cool thing to have, because you're running the show, you get to do it the way you want. What also means there's also a lot of responsibility. It also helps to have an alternate net control in case something happens to net control station number 1. You would be amazed to know that sometimes sometimes someone's battery will die right in the middle of a net, in which case somebody else has to jump in. Okay, which of the following is a characteristic of good traffic handling? That would be passing of messages exactly as received. So if you lose the word not, that's a big deal. If there's something that you don't know how to spell, It's not a common word. For instance, if let's say I'm going to use Sue as an example here. Cutsa George is not the most common last name. So if I'm saying, here's the name, first name is Sue, Sierra Uniform Echo, last name Cutsa George, I spell Charlie Uniform Tango Sierra Oscar Golf Echo Oscar Romeo Golf Echo. Please confirm with a phonetic spelling of that name. Over. So I would ask for somebody to verify that they got it exactly as I spelled it.
I've been doing that my whole life, but not with all the phonetic alphabet. So
yeah, so phonetics are great. They're also great when conditions are lousy, because a G and a T and a B and a C and a P all kind of sound the same when conditions are bad. Okay, preamble of a formal traffic message contains information needed to track it. The check of a message is the number of word or word equivalents in the message. So if I say, I am not going today, I am not going today, the check would be 5. If you got 4 words, you might have dropped the word not. And then you'd say, please repeat message, because my check didn't match. When do the FCC rules not apply to an amateur station? And that would be never, no matter what you're doing. An amateur station or amateur station control operators ever permitted to operate outside of the frequency privileges of their license. Okay, this is going to come up over and over and over. Basically, if there's a bona fide emergency, like a threat to human life, an imminent threat to property, you are allowed to do whatever you need to do to achieve safety. That could mean, there's a police car that's sitting there and a policeman is, going and dealing with something, and you need to get somebody's attention. You can go over and use the police radio. You probably have to explain why you did it, but if there was no other means by which to get some help, you do whatever you need to do. Okay, amateur satellite operation. We have lots of satellites up in space. We have launched our own satellites. They are floating around at about 200 miles up in the air. Many of them are beaconing down information. Some of them are carrying onboard repeater stations, which receive and retransmit signals. Okay, so what does it take to make contact with the International Space Station on the 2-meter band and the 70-centimeter band? So as a technician class operator, the reason that this is said is because, Sue, as a novice, you do not have access to those bands. At least not yet. But when you upgrade to technician, then you will. So any technician or higher class licensee can transmit on the 2-meter band or the 70-centimeter band and point their signals up into the sky and talk to satellites, including the ISS. A satellite that is operating in mode UV, that would be UHF up and VHF down. So there's an uplink and a downlink. What modes are used by satellites? Most of them use FM, but not all. There are some that do Morse code. There are some that do data, like packet. There are some that do single sideband. They use something called a linear translator and can operate using CW and single sideband. The impact of using too much effective radiated power on a satellite uplink, it's the same thing as always. If your signal is super, super loud, nobody else can hear anybody else. So you basically, by transmitting with too much power, you block access of that resource to other people. And how can you judge if your uplink power is too high or too low or just right? Basically, your signal strength on the downlink should be about the same as a beacon. So a satellite, as it's zipping around the Earth, it's basically saying, here I am, here I am, here I am. Let's say once a minute. If you transmit up and you hear yourself come down, your signal should be about the same strength as the satellite, indicating here I am, here I am, here I am. Okay, LEO is a LEO, low Earth orbit satellite. Most amateur satellites, because of the lack of space for geostationary satellites and the extreme expense of putting satellites up at 22,000 miles. Costs a lot of money to get them up there. Most amateur satellites are LEO or low Earth orbit, including the International Space Station. What is a satellite beacon? That is information from a satellite that has status information. Here I am, here I am, here I am. Oh, by the way, my battery's at 75% charge. I'm in full sun and it's minus 226 degrees outside. That would be information from a satellite beacon. What telemetry information is typically transmitted by a satellite beacon? That would be health and status of the satellite. My solar panels are at 75%. I'm in full sun. Inside, it's a nice warm 22 degrees Fahrenheit. Outside, it's minus 226. Who can receive telemetry from a space station? Telemetry, that word, tele, meaning distance, metry, meaning meter or measurement. So basically, who can actually receive information on what's happening with the satellite? That would be anybody. You do not have to be licensed just to listen to it. Which of the following are provided by satellite tracking programs? So you might find a map, and actually I'm going to bring up AMSAT satellite tracker. And so you'll have information on the satellite, and you'll have a current position. You'll have these things known as Keplerian elements, which will come out of, which define exactly where in an orbit a satellite is and what the orbit's going to look like. And let's see what CN84, which is where we live here. Oh, stop it. There we go. So here are the next 10 passes for the International Space Station. I can also view the current location and where it's going to be. And look at that. It's actually going to go right overhead. Wow. When's that next pass? That would be October 10th. Ooh, it's a good pass too. It's almost 11 minutes long. And 12 o'clock. It's going to be right at 12 o'clock. So maybe we'll even get to listen to it. Who knows? I'll turn on the radio and listen to it. I can actually pick it up on a handheld.
My dad, can you guys hear me?
Yep.
Yes. My dad, since he's a ham, he once called the ISS,
Yep.
but he couldn't reach it because he had a small ham, or the astronauts weren't awake, like the ones that were hams.
They also have a repeater set up. So let's see, AMSAT, satellite status, Oscar satellite status. Let's see, ISS is in, oh, it's not on right now. It's red. All right, so even if it does go overhead, we couldn't work it. So, oh well. That means they're off doing something else, or they just shut it off for the day. That happens sometimes. Okay, so time, azimuth, elevation of the start, max altitude, end of a pass, apparent frequency of the satellite transmission, including Doppler shift. So Doppler shift, as a race car goes by, sound of a fire truck as it passes you changes, the pitch changes. Satellites are moving at 17,000 miles an hour and are actually going fast enough that they will Doppler shift the radio frequency, which is traveling at 300 million meters per second. They will actually cause a shift in the radio frequency because they're traveling so fast. So you actually have to change the tuning on your receiver a little bit at a time so that it stays in tune. Again, Keplerian elements are inputs to a satellite tracking program that essentially allow you to figure out where a satellite is going to be and when. Again, a Doppler shift is an observed change in signal frequency caused by relative motion between the satellite and the Earth station. And spin fading. Okay, we talked about this very briefly yesterday. Essentially, if this is a satellite, here's the antenna on the satellite. satellites normally spin as they're in space. As it moves away from you, the antenna can actually be blocked from your view. And that would be known as spin fade. But don't worry, it'll come back. Okay, operating activities. We're on page 77. There are many different ways to have fun with amateur radio. It is not all work. Once you've put together a station, you might as well use it for enjoyment as well. One thing is called rag queuing. Rag queuing basically means to sit around and just talk to people and talk and talk and talk. And that's again known as rag queuing. For some of us, we really enjoy something called contesting. Contesting is an activity which basically means making as many contacts with as many stations as possible during a specified period. So to give you some idea of what contest calendar looks like, these are all the contests of the following week. So notice we are just finishing Nevada QSO party. There's an Oceania DX contest for Morse code, Pennsylvania QSO party, Arizona QSO party, South Dakota was this weekend. And then we have a few during the week. And then next week, there's the New York party. And then the following week, there are probably, there's a good number more. Oh, school club roundup that lasts for an entire week. And then, oh, look at that, the EME contest. That's moon bounce. There's a weekend long moon bounce contest. This sprint contest, that's only about what, 10 hours long. Oh no, not even. That's only it's only 4 hours long. That's a short one. So there's a lot of on-air activities that you can participate in. There are also special events, such as the Route 66 thing, where the different clubs that have stations that are along the old Route 66 will, for like a week, all set up stations along Route 66 and participate for an entire week. And one of the goals is, if you're one of the people hunting them, you try to work all 25 stations along Route 66 and get a certificate for having worked them all in a given year. So lots of activities. When you're contesting, if you're in a contest, send only the minimum information needed for proper proper identification and the contest exchange. So Pat, I'm going to call CQ, and the exchange is your signal report and your state. CQ contest, November 7, Juliet, India contest.
This is Alpha Alpha 8 Juliet.
Alpha Alpha 8 Juliet, 59 Oregon.
Thank you. N7JI, you've got a 59 coming in here as well. Also, this is Michigan. Back to you. This is Alpha Alpha 8 Juliet.
Alpha Alpha 8 Juliet, AAHA, thank you, November 7, Juliet, India contest. So actually, you were really verbose.
Yes, I know, because you put me on the spot, and I haven't had my HF antenna up for a while, so I'm out of practice.
Yeah.
So it does take practice.
It does, but it also, you're basically entering them on a keyboard. You're typing into your computer log. You get used to operating in a very fast mode.
And I listen for a while before I start contesting.
Yeah. Yeah, you sort of pick up the flow.
Scott, can you explain 5.9?
Yeah. Okay. So there is a signal report, and so here is in Morse code, it's your R, S, and T. In voice, it's your R and S. R is readability. That's from 1 to 5. S is signal strength, 1 to 9, and tone, which we only use in Morse code, is 1 to 9. This is the reason that we use the tone on Morse code is because you might have chirp or buzz or hum on your signal, depending on this has been used these have been used for a long time. So typically today, it's very, very unusual to find anybody who has a tone of anything less than 9, because there's a lot of good equipment out there. Every so often you'll hear somebody with a dying battery that's portable that they sound whoop, 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 whoop. That would be a tone of not 9. During a contest, it doesn't make a lot of sense to give anybody other than anything other than a perfect report. So Morse code, everyone's a 599. And on a phone contest, everyone's 5.9. Although yesterday I did actually get a 5.6. And I had to go into my program and say, no, it really was not a 5.9. It was a 5.6, because nobody gives anything but a 5.9. Even if they can barely hear you, you're still 5 and 9. So, which is a perfect report because they heard you.
And when you sign off, on an internet message, I noticed 73.
Yep. 7.3. It's actually, you say it as 7.3, not 73 or 7.3s. 7.3 comes from Morse code. Da 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 da. And it means best regards. Shorthand for best regards. And see you later.
Thank you.
Yep. Okay. What is a grid locator? So in your packet that I sent out, you should see a grid square map. And as part of the grid square map, does everybody see that?
Mm-hmm.
Okay. You notice that there are, let's see, grid square map. Where is that? Here we go. US grid square map. So part of the US grid square map is that every one of those rectangles, they're not actually squares, is 2 degrees 2 degrees wide and 1 degree high on the world map. So 2 degrees of longitude by 1 degree of latitude. I happen to be in CN 84, and I'm guessing that Pat, you're in EN 72. Is that right?
Yes.
So
look
the
it up
reason
on-
that we do that is because for VHF purposes, states are big things to aim for. Grid squares are much smaller things to aim for. So it helps in pointing antennas and identifying to within a smaller area your actual location. Nate, I see your hand up. Hello, hello. Hello, Nate. There we go.
I've been checking my emails because you said you sent me the link to all these, and I can't find the grid or any of the things you want me to have. I can't find any.
Okay. So that means maybe you didn't get the maybe you didn't get the zip file. Okay, stinky feet. It should be there, but I'm going to send it again.
Thanks.
Now, let me just attach it and send it.
I've got my grid square if you want to. I found my card.
EN 72.
No, actually it's EN71JW.
Oh, so you're in the very northern part of EN 71.
Mhm.
Okay. And I'm in the very southern part of CN 84. So, okay.
Wait, what was the second set of, so I heard, I was looking at my grid square here and I'm looking where Pat said I can see where it says EN.
Yep.
And then I can see the 71 and then she said JW.
Right. Actually, that is that's a subset of it.
So that's another page deeper within some document somewhere that we don't
Yeah.
know yet.
Right.
All right.
They're
and-
really small. Each grid square that you see is actually split up into 24 by 24.
Okay.
So it goes from AA to XX.
Okay.
And that gives you even more granularity, indicating exactly where you are. I mean, I'm actually in CN 84 Lima Alpha, but no one needs to know that for the most part. You know, I rarely ever need to use it. Okay, so let's see. Continuing, there's our grid locator. Which of the following methods is used to locate sources of noise interference or jamming? That would be radio direction finding. We also do radio direction finding for fun. We hide a transmitter in a field and we have everybody go find it using handheld radios and portable antennas. It's not even a transmitting thing. The transmitter is transmitting, but you're not. You're just basically listening for it. Which of the following is useful for a hidden transmitter hunt? That would be a directional antenna, typically handheld directional antenna. What is IRLP? That is the Internet Radio Linking Protocol, which allows us to connect radios and repeaters over the internet using voice over internet, or VoIP. VoIP is a method of delivering voice communications over the internet using digital techniques. What's cool about this is that when the internet is working right, this allows us to take repeaters from far, far away from each other and connect them together. So it's kind of a hybrid communications method. Before using Echolink to communicate over a repeater, you have to register your call sign and provide proof of your license. How to obtain a list of nodes that use voice over internet protocol. You subscribe to an online service, a repeater directory will typically have it, and looking for that online repeater list maintained by the local frequency coordinator. So if you remember, we on our listing for our repeater, it actually lists Echolink. If it was connected to IRLP, it would list IRLP connection and potentially indicate exactly how to find it, you know, what node to connect to.
Question?
Yeah.
When you say Echolink license, does it just mean that Echolink needs to know your FCC license?
Yep.
Or that you need a separate Echolink license?
Nope, here's Echolink. And in order, you can download the app, but in order to activate it, you have to have the activation code, which they will give you once you provide them proof of your license.
But so it's really just your FCC license?
Yeah.
Okay.
How to activate a repeater's IRLP link. Notice this right here. In addition to being used for frequency entry, once you have the push to talk button pressed, this will transmit DTMF or touch tone codes. Every handheld radio will have that. This allows you to basically send out a series of codes. I could use that to shut off a repeater or change its operating mode, or also connect to a local gateway, for instance. What name is given to an amateur radio station used to connect other amateur stations to the internet? That is known as a gateway, just like on the computer. Okay, so we're into the home stretch here, page 79. What agency regulates and enforces the rules for the amateur radio service in the US? That would be the FCC. We already discussed some of the purposes of ham radio existing. Advancing skills in the technical and communication phases of the art is one of the big ones. What is Part 97? Does everyone remember what Part 97 is?
That's the part that the hams operate under.
That's right. That is the ham radio rules. That is the rule book of the FCC. It's in the Code of Federal Regulations, and Part 97 is what it's called. Okay, what is the definition of a beacon? A beacon is an amateur station transmitting communications for the purposes of observing propagation or related experimental activities. So a beacon is a transmitter only. There is typically no receiver on a beacon. It's just basically saying, here I am, here I am, here I am. Try to listen for me. So it might be on a mountaintop somewhere, solar power, and somebody gets to visit it once a year, and it just basically transmits its call sign over and call sign and location over and over and over. And if you can hear it, that means there's propagation between it and you. A space station is any amateur station located more than 50 kilometers above the Earth's surface. When are you allowed to willfully interfere with another ham station?
Never.
Never. That's right. That would be called malicious interference. A volunteer frequency coordinator is a person who has been selected and recognized by local hams who are eligible to set up repeater stations. So volunteer frequency coordinator is a really thankless job, but it's an important job. They're the ones who assign repeater pairs and make sure that you don't have conflicts. And amateur operators in a local or regional area whose stations are eligible to be repeater or auxiliary station operators are the ones who select or vote for the frequency coordinator. And again, we do that so the FCC doesn't tell us exactly what to do because we don't want that. All right. The International Telecommunications Union, or ITU, is an arm of the United Nations that deals with information and communications technology. They are the ones who basically say, hey, United States, all your call signs have to begin with WN or K or AA through AL. The FCC then gets to distribute call signs and administer them. But the ITU is the one who says that all British call signs start with the letter G or the letter M or the number 2, which is true. Okay, which frequency is in the 6 meter band? Okay, everybody pull up your by the way, Nate, did you get the zip file? Okay, everyone pull up your frequency spectrum chart. And we're going to say what frequency is it? What are the frequency limits on the 6 meter band? Everybody? I'm
50 to 54.
50 to 54. Very good. And I'm going to pull that up myself and hopefully put it up on the screen if I can find where it is on my computer. What a pain. There we go. All right, so let me put it up. Band plan. Sorry, this is taking a little while. A little slow today. Okay, there we go. Oh, stop it. Now Zoom is complaining. There we go. Okay, 6 meter band. Here's 50 to 54 megahertz. What are the limits on the 2 meter band?
$144.
Yep, to 148. Okay, now it is also important to note that this is in ITU Region 2. We are in Region 2, North and South America, the Americas. Region 1, Region 3 are in different parts of the world and have slightly different rules. If you go to Alaska or Hawaii, your rules are actually a little different. You use your American call sign, but the overlying rules are a little bit different. So let's see. Why should you not set your transmit frequency to be exactly at the edge of an amateur band or subband? The big one is that you don't want your signal to be outside of the legal limit. And we kind of covered that yesterday, that if you know that you're on upper sideband, your dial frequency is such that your signal will extend 3,000 hertz above that dial frequency. If you're at, for instance, let's take a look down here at 20 meters and go to 14.350 and you set your frequency right at 14.350, your signal will go all the way up to 14.353. Is that in the ham band? Yes or no?
No.
It is not. Therefore, you cannot do that. You can go up to 14.347 and be fairly sure that it's going to be in the ham band. You can go to 14.345 and be really sure that it is. So the other reason that we do that is to allow for transmitter frequency drift. Again, the display is different than what's actually coming out of it. And the other one is that there might be calibration in the transmitter frequency display. Again, what's on the display is not what's coming out of it exactly. These are usually very small, but with older equipment, they can be very, very pervasive. Okay, so it doesn't even show up on this chart, believe it or not. Notice that the 1.25 meter band goes from 221 to 225. Well, it used to go from 220 to 225. And the FCC made a deal between hams and UPS, believe it or not. If everybody's ever seen one of those brown tablets that they use to scan and register packages, those actually operate on what used to be a ham band. And because of that, we gave up 220 to 222, and they gave us 219 to 220. This is right in the middle of page 81. That band can only be used for fixed digital message forwarding systems. That's it. That's the only thing we can use them for. And I think the big reason for that is that that is a shared band with somebody else. So that's the only thing we're allowed to use it for. And there are very, very few stations that have been set up for that. But that is one of the rules, that between 219 and 220, by law, we are only allowed to operate fixed digital message forwarding systems. On what bands does a technician class operator have privileges? Let's take a look at our chart. And you notice down here, you have on the 10-meter band, it says novice technician voice, 28.3 to 28.5, and you can also operate from 28 to 28.3 using Morse code. So there you go. You have phone privileges, which are that blue hatched thing on 28.3 to 28.5, which is on the 10-meter band. Which of the following bands have frequencies available to technicians for teletype and data? Right here at the bottom end of 28 megahertz, which is the 10-meter band. So the answer is the 10-meter band. Which of the following VHF, UHF frequencies are limited to Morse code only, CW only? So the only ones that are limited by law are 50 to 50.1 and 144 to 144.1. Those are the only ones that are actually codified in the rules that say Morse code only. On the high frequency bands, how much power can you as a technician class operator use in any of these bands? And the answer is 200 watts. I have never had a transmitter that operated at 200 watts. So this is rarely an issue, but it basically means you can't run a big amplifier. However, this is another reason why you have to get licensed, because in addition to being able to build your own equipment and use it on these UHF and VHF frequencies, anything above the 30 megahertz threshold, you are allowed to run 1,500 watts of peak envelope power, which is a big amplifier. Amateur radio operators also share some bands with users from other services, such as the 70 centimeter band. Notice we have from 420 all the way up to 450 megahertz. We are actually secondary users of that band, which means that somebody else is primary. That primary user happens to be the US military. And on the 433 megahertz band, right there, there's also industrial, scientific, and medical stuff. So basically, you might hear other things floating around on this band. And if we are asked to not interfere with them because they're primary, we have to shut down our operations. Okay, so we are now on page 83, operator classes and stuff like that. Okay, you have 3 license classes that are available from the FCC. You have your technician, your general, and your extra. An FCC license is good for a period of 10 years. There is something called the FCC ULS, which is the Universal Licensing System. If you signed up to take an exam, you had to go on the ULS and create a federal registration number or FCC registration number. So you've already experienced the FCC's database. When can you operate? As soon as your license shows up in the database. It used to be that possession of a piece of paper was basically what said that this is your permission to operate. And this is not true anymore. You do not need the piece of paper. You don't need to actually have the piece of paper. You just have to have access to the database and be able to say, here's the database on my laptop. Here's the license. How many operator and primary station license grants can be held by any one person? The answer is 1. What is proof of possession of a license? It must appear in the FCC ULS Consolidated Licensee Database. And Nate is raising his hand.
Is it too late to sign up for the exam yet?
No. It's not going to start till at least 1 o'clock, so you'll have a nice break in there. Okay, who can select a desired call sign under the vanity call sign rules? That would be anybody who has a license can sign up for a vanity call. As of right now, it is still free to do so. You are only eligible to select a vanity call that is for your license class. So if I held a technician class licensee, I could sign up for licenses that are of the form. That would be K1 ABC. That would be a 1x3 because American licenses have to start with W and K or AA through AL. And the way they're set up is there's always one number and 1 or 2 letters and 1, 2, or 3 letters. So anything that's a 1x3 or a 2x3 can be requested by anybody with any license class. A 2x2 can be requested by an advanced or an extra. A 2x1 or a 1x2 can only be requested by an extra class operator, which is why Pat has a very cool call sign AA8J, and I have N7JI. Those both fall in the extra class pool. There are also licenses that you can get temporarily, such as K6W, which is a 1x1. Those are used for special events, such as let's say a public service event or a 100th anniversary of something, things like that. There's a grace period following the expiration of a license. You can renew it for up to 2 years. It'll remain inactive in the database and it won't be purged or eligible for somebody else to get for another 2 years. If your license is expired and still within the allowable grace period, can you continue to operate? The only time you can operate is if your license is active. If it says active in the database, you can use it. So if you are in the grace period, you are not active, you are inactive, you are not allowed to operate until you send in a new application to the FCC and it becomes active.
Do you have to take a new test?
No. In fact, let's say you had an extra in 1965. In order to get the extra back, you have to just take a technician exam now and show proof that you held the license in 1965. So greatly simplified. Clubs may apply for a station license for their club station, which may apply even for a vanity call sign. In order to be a club and apply for a club station license, you have to have at least 4 members. So that would be, your standard as far as president, vice president, secretary, and treasurer. When are you allowed to operate your license with your station in a foreign country? Basically, if the other country says it's okay. I've operated in Chile, I've operated in Norway, Finland, Austria, Uruguay, Turks and Caicos, Canada. So basically, if you get approval to operate in those countries, you can operate. With any licensed station can.
What does approval mean?
Approval means in some cases that there's a standing agreement and you just have to print something out. In some cases, you actually have to apply. You actually have to get an inter-American radio permit, like with Chile and Uruguay. And in some cases, like Turks and Caicos, you actually have to apply to their Ministry of Communications and send a copy of your license and $35. So it depends, it changes from country to country. Okay, from what of the following locations can an FCC licensed amateur station transmit? If you have a US flagged ship, that is technically the part of the United States. If you get the captain's permission, you can operate from that ship. As a licensed ham, it's okay. We're on page 86. As a licensed ham, it's important to know what you can and can't do on the air. What is considered indecent and what is considered music. Okay, are you allowed to do indecent or obscene transmissions over the airwaves? We are beholden to these same rules as TV and radio stations. We can get fined just like they can. So you've got, like, for instance, I have my radio vocabulary and I have my everything else vocabulary. They have to stay totally separate. I work in an industrial environment. That environment, the language that I use there is not appropriate for use on the radio. Sometimes. Under what conditions is an amateur station authorized to transmit music using phone? We are never allowed to do that. The only time that it is permitted is, and this came from the days of the space shuttle when they used to wake up the astronauts using music. There were retransmissions of space shuttle audio over the ham bands. That music was allowed to be retransmitted. So basically, if it's up and down between a spaceship and a ground station and there's music, that's okay. That's the only time. We have lots of stations that transmit music. We are not them. When can you transmit messages that are designed to encode their meaning, to hide their meaning? And there's only 2 times when we can do it. When you're talking to another person, definitely not. The only time you're allowed to do it is when you're transmitting control commands to a space station or RC craft. We can run, for instance, we can fly remote control aircraft. We can fly pretty big remote controlled drones. We can do remote boats. We can do remote cars with very long range and a watt of power, which is actually quite a bit. We can also run our own satellites and change the satellite mode of operation. In order to make sure that doesn't fall into the wrong hands, we're allowed to encrypt our communications, but only for those purposes. Any country whose administration has noted the ITU, which again is a part of the United Nations, that it objects to communications with another country, can do so. So we are allowed to talk to anybody, even North Korea right now. However, for instance, there was a group of hams who did a de-expedition in, I believe it was Oman, or no, it was Yemen. It was Yemen. And they were specifically said, it's fine for you to operate, but you can't talk to Israel because we're technically still at war with them. Nate.
What does ITU mean?
International Telecommunications Union. It's part of the United Nations. Okay, when is a teacher allowed to make money for teaching with ham radio? So basically, a teacher is the only person who's allowed to make money using ham radio, but only if it is incidental to education. It's a great educational tool, but we can't like go on the air and earn lots of money. There are lots of other ways to do that. That's one of the reasons our licenses don't cost anything, at least for the time being. So if you're teaching a class and you use ham radio, you can still collect your salary. When are you allowed to notify other amateur stations of the availability of equipment for sale or trade? Basically, if you don't do it like on a daily basis, you're not advertising pizza at your pizzeria for sale. Basically, if it's used in an amateur station, hey, I have a handheld that I'd like to sell, that's fine. You can even post a price. You can even exchange, you can even haggle over the air with it. Probably better to use the phone, but it's legal to do it. What is meant by broadcasting? We do one-way transmissions. Broadcasting is information that's intended for the general public. We are not the general public. We are hams. So when we transmit bulletins and things like that, we are intending them to be for the amateur population, which is one-way communications as opposed to broadcasting. So we don't broadcast. So a broadcast is a transmission intended for the general public. When are we allowed to deal with broadcasting? Program production, news gathering, assuming that there are no other means available. We're in the field, somebody comes along and says, I need some kind of link back to my news outlet. I need to get some information to them. And there's that thing again. Only where such communications directly relate to the immediate safety of human life or protection of property. So there's a dam about to break. That would be absolutely fine. Use your radio. You can even have somebody send information, directly over the airwaves. When are we allowed to make one-way transmissions? One way, as opposed to a broadcast, because it's intended for amateur radio use. That would be code practice. No one's going to respond to code practice. Information bulletins. The ARRL transmits information bulletins using digital, using voice, and using Morse code every single day of the year. And transmissions necessary to provide emergency communications. Attention all amateur radio operators. Interstate 5 is closed for a major accident at milepost 215. We hear that all the time out here. What is allowed? Communications incidental to the purposes of the amateur radio service and remarks of a personal character. So that would be, so how you doing? How's the weather? How's your sciatica doing? You know, you hear that a lot. And I used to laugh at that, except that, you know, now I'm in my 50s. And you know what? The fact that I have sciatica, I'm going to talk about it with my friends. So, but I remember when I was younger and we used to laugh at everybody who would get on the air and talk about their doctor's appointment. Well, you know, it's a big deal. That would be remarks of a personal nature. We also talk a lot about food. We talk a lot about bicycles. We talk a lot about being on the radio, building antennas, stuff like that. There are certain things that you probably don't ever want to get into too much. Religion and politics, just like everything, you know, you want to keep it so that it's friendly. You want to keep it so that it's fairly genial. Religion and politics, you tend to shy away from. When is it? Okay, we are now on the absolute home stretch, page 88. When are you allowed to transmit without a control operator? Okay, the control operator is the person who is responsible for what is coming out of the station. At a TV station, there's a control operator. That's the engineer who's responsible for the transmitter. At our station, the control operator is the person who is literally in control of the station. So you are never allowed to operate without a control operator, ever. So there are different forms of control. Usually the person who is licensed to operate the station is assumed to be in charge of the station and thus the control operator. However, that's not always true. Let's say that I am out of town and my friend wants to use my station. I can say, okay, you are the control operator while I'm out of town. And I will basically say, you're the control operator.
But they have to have a license.
They have to have a license. That's right. When the control operator is not the station licensee, who is responsible for proper operation? And that would be both the control operator and the station licensee. So just because you've walked out of town does not absolve you from blame if your equipment starts failing, because it's still yours. Similarly, if I take this radio, technically, I am the owner of this station. This is actually a radio station. It's very self-contained and portable. If I loan it to somebody, in theory, because I am the owner, if I loan it to another ham and it starts malfunctioning, it's still kind of my fault. It's their fault too, but it's kind of my fault because I'm the station licensee. Let's see, who is accountable should a repeater inadvertently retransmit communications that violate the FCC rules? Somebody gets on a repeater, keys it up without a license, and starts cursing on your repeater. You wouldn't think this does happen. Occasionally it does happen. Somebody just decides they're going to just open up their microphone and lay down a carrier right on your repeater and hold it open for 10 minutes for no reason and not identify. They've got a grudge against somebody, they're bored, who knows? The repeater owner is not responsible for that. That is the responsibility of the person doing it, because the repeater is in automatic mode. Now, if I'm the repeater owner, if I'm the trustee of the station, yeah, I probably want to get on and go through the back channel to the repeater and hit the kill switch remotely and turn it off. I don't have to if I'm not listening at the time, but it's not a bad idea to know how to do that. What determines the transmitting privileges of an amateur station? That is defined by the person who is the control operator. So if I am a control operator and I have a technician class license, are we allowed to operate in an extra class band? Yes or no? And the answer is no, which is why it is a really good idea to have a trustee of your station, if it's a club station, who has an extra class license. Now, it does not mean that just because the trustee is an extra, if the control operator is a tech, they can still operate as an extra. What it means is that it makes using your call sign a lot easier. So let's see, who can be the control operator of a station communicating through a space station or amateur satellite? The answer is anybody whose privileges allow them to transmit on the uplink. So sometimes you will find that there is a repeater that oddly enough has 2-meter uplink and 15-meter downlink somewhere over here. So if I'm transmitting on 2 meters with a technician license, am I legal? I am, sure. But what happens if it comes down on the 15-meter band? I don't have any privileges there up around 21.275.
So you're not even allowed to listen?
Oh yeah, you can. Anybody can listen to anything.
So isn't that what you're doing on the downlink?
That's exactly right. The repeater is what moved your signal, so you are not responsible for that. So you transmitted legally on the uplink, and wherever it ends up on the downlink is not your responsibility. It's the repeater's responsibility. So that's why it's perfectly legal to do that. Control point and control type. Okay. What is an amateur station control point? That is the point from which control is obtained. This on my handheld radio, this push to talk button is the control point. This would be known as local control because it is in my local control. I am controlling this locally. It is in my hand. Automatic control. A repeater operates automatically. So therefore it is under automatic control. That is a different kind of control type. Remote control. That would be, for instance, operating a station over the internet, which we can do. Basically, what that means is that the operator must be at the control point because you can never have an amateur radio station that's operating without what?
An operator?
An operator, a control operator has to be there. So if you're operating remote control and you're transmitting, you cannot walk away from your station while it's transmitting. Well, if you're using it over the internet. A control operator is required at all times, and the control operator indirectly manipulates the controls using the computer. Okay, when do you have to identify? Every 10 minutes and at the end, which is why when you turn control back to net control, you say N7JI, back to net, because you don't know when the next time you're going to transmit is. You do not have to identify at the beginning of a transmission, oddly enough. Most people do, but you're not legally required to. The only time you don't have to identify your station is when you're transmitting with a remote control, let's say a Futaba controller that's transmitting digital signals to a remote control car or boat or drone or airplane or something like that. You have to mark the transmitter with your call sign and name and address. And you're typically limited to 1 watt. And most of those operations are on the 6-meter band. There's a section of the 6-meter band that's set up for remote control. What's an acceptable language for station identification when operating on phone? Phone is voice. That would be English. I have operated in Chile and Uruguay. When you're operating there, even if you're speaking English, you have to identify your station in Espanol. Noviembre 7 J India Diagonal Charlie Echo 5. I had to identify my station in Spanish. What method of call sign identification is required for a station transmitting in phone? You can speak it, or you can actually have in the background Morse code identifying your station. That's how a lot of repeaters work. What are the FCC rules regarding the use of a phonetic alphabet? The phonetics are really encouraged. You don't have to do it, but they're really helpful. When identifying your station during tactical operations, for instance, I am race headquarters, how often do you have to identify your actual call sign?
Every
Let's
10
see.
minutes and at the end.
Every 10 minutes and at the end. In other words, even if I am aid station 6, aid station 4, Red Cross tent, I still have to use my call sign. And I still have to do it legally at the end and every 10 minutes during. So let's see, a self-assigned indicator, N7JI/5. That means I'm operating in Texas, for instance. I do not have to identify that, but I can. And I can actually say stroke, slash, or slant. Those are both, those are all valid ways of doing it. N7JI/6 means I'm in California. Now, if I'm in Canada and I do N7JI/VE3, that means I'm in Ontario. Am I required to do that if I'm doing it in Ontario? I actually am, because I'm operating in a different country.
That's right. I forget.
Yeah. Okay, here we go. What is meant by third-party communications? Nate, you got your hand up. Good segue.
It means you are speaking on behalf of a licensed ham radio operator.
Right. Well, actually, or they're speaking on your behalf, or you're actually giving a message under their call sign.
I know that because I do it with my dad a lot.
That's right. And actually, my kids both did it before they became licensed. So basically, a third party is if Pat and I are talking to each other over the radio, for instance, and we each have somebody here who is unlicensed, we can actually let them talk to each other directly or pass messages on their behalf. And that would be known as third-party communications. This was actually really widely used during the Vietnam War, when the hams would run phone patches. There was there's a group called the Military Affiliate Radio System, or MARS, that would set up stations in Vietnam and various different hams in the United States who would make contact with each other and then allow soldiers, because there were no phones that worked, to make phone calls and talk to their families at home. That would be third-party operations. Now, it is also true that the United States doesn't have third-party communications with every other country. There are only a few countries in the world that don't allow it. Typically, those are in Europe and Japan, and a few others, actually. So within the Americas, third-party communications are actually very common. We're only allowed to do third-party communications within the United States and Canada, or between the United States and other countries where we have an agreement. And the very last question, when does the station licensee have to make the station and records available to the FCC if they show up at your door?
Yes.
Yes, the answer is yes. Whenever they show up at the door, you have to let them in to see your station, because they're obviously looking for something. It is a very rare instance that the FCC will come knocking at your door for no reason. So if you haven't given them a reason, they probably won't show up because that costs money and they don't really want to spend any money on us. So unless they suspect that there's a ham station that is interfering with, let's say, air traffic control or something like that, they're actually very good at finding those things. They're very good at doing triangulation and can figure out exactly where it's coming from. So I don't personally know anybody who's ever been visited by the FCC, but you have to let them in if they knock at the door. And do we have any questions? It's 12:15 and we're done.
Are we?
We're done.
Thank God.
Oh, been excellent.
Now let's just take the test and get it over with.
Yep, it's a lot of material. Well, as I see it, the test is taking the test is then the gateway to actually getting ready to learn stuff, because then you can actually use it, and that's when it gets fun.
I got 315.
What?
I got 315.
315? Oh, that's right, because you're in Florida, right?
I got 315 as well.
Yeah, well, it's 12:15 here. So
When is the test?
it starts at 1 o'clock my time. So do you have all the link, Pat? You have all the links and everything?
Yes.
Oh, good. Congratulations.
Signed up. I've been accepted, and I will be a VE.
Yay. So it is quite possible that Pat, everybody, is going to be one of your volunteer examiners. So thank you, Pat.
Do you know
So
if it's going to be a real problem if you don't have a second video camera?
There needs to
Yes.
be a second camera. But that can be that can be a phone, that can be an iPad, that
Oh,
can be
okay.
literally anything.
Yeah, phone will work. I just wasn't sure. Okay.
Yeah, no, phone works great. Typically what they do is.
Do I need,
What?
do I
No,
need one?
you don't need one. You just need the one.
So
What you're
Scott,
doing. Yeah.
this is Tom. I'm going to be heading across town to take the test. And so if I'm not there exactly at 1, then just, I'm assuming there'll be other people ahead of me and I'll, just don't panic. I'll be
Yeah.
there.
Well, the way that it'll
But I
work
also
is
won't
that,
be on my phone. I won't because it is a landline number I gave. And so you won't be able to get hold of me that way.
okay. The way that it works, I would send Kent a note, or I can send him a note for you. Do you
I'll
have a,
probably be there just fine, but I just don't want to you to panic if I don't show up right on time.
okay, so a better number for Tom? Do you have a cell phone number to give?
No, you can just send me I'll have email and
Okay,
that'll be fine.
okay. He's got.
You were gonna say the way it works?
Oh, yeah. So the way it works is that basically you'll go into a prep breakout room from Zoom. And we'll have somebody who's there who basically works you through getting your computer ready and your camera ready and your phone ready or whatever. And then from there, you'll just you'll end up in a room with three or four, probably 4 examiners. And you'll just be asked to, go around the room, show the ceiling, show the floor, show the walls, show your scratch paper, stuff like that, and then go.
What if your office is pretty cluttered?
Well, I wouldn't. Well, can you show me your office?
Well, in my case, I go across town.
Oh yeah, it'll look fine. That'll be fine. If there's nothing that
I can out clutter you.
Yeah.
I didn't
What
know.
about mine?
Yeah, that'll be okay. Well, here's something that we often do. Somebody will say, "Oh, you know what? The cleanest room in the house is my bathroom," and they'll actually go take the test in the bathroom.
Fine.
So, yeah, we'll work it all out. We haven't. I don't think we've really found anything that we can't overcome.
I have dual screens, but I can turn one off. Yeah.
Yeah, that'll probably be asked for. And actually, one of the cameras will typically be behind you, and we'll be able to see the screen and your hands. And you have the webcam over here, and then another one looking in from, let's say, over here.
Okay.
Yeah, it's pretty smooth. It works well. So if you haven't taken many practice exams, go try a couple, and we will see you then. And if any other questions, now's a good time to ask.
Will you be emailing out a link to the videos?
I will. Yes, actually, I actually got the first one up on YouTube last night, and it was big and took a long time to put up, but yes, I'll be sending out a link.
Thank you.
Mhm. All right, I'm going to stop recording. Goodbye.
Bye.